From emptiness came everything, a spark from absolute nothingness. The universe, our reality, exploded from a single moment smaller than an atom, yet powerful enough to birth galaxies, stars, and life itself. It defies imagination. Scientists, stunned by the cosmic puzzle, describe a moment when the laws of physics emerged from absolute void. Quantum fluctuations, elusive forces, and particles that blink in and out of existence. It's a creation story more incredible than any myth. Can something truly arise from nothing? In the context of the universe's origin, nothing is a concept that challenges our everyday understanding. It's not simply an empty space or a vacuum, but rather the absence of everything we can conceive of. No matter, no energy, no space, and no time. This absolute nothingness is difficult for us to imagine because our minds are accustomed to thinking in terms of things that exist within our universe. Physicists and cosmologists grapple with this concept when discussing the potential state before the Big Bang. However, even the idea of before becomes problematic when we consider that time itself may have come into existence with the universe. Some theories suggest that quantum fluctuations can occur in this state of nothingness, potentially giving rise to something, in this case, our entire universe. The notion of nothing in this context also raises philosophical questions about existence and non-existence. It challenges us to consider how something can come from nothing, a puzzle that has intrigued thinkers for centuries. Some scientists argue that the total energy of the universe might actually be zero, with positive and negative energies perfectly balanced, making the transition from nothing to something more plausible. Understanding nothing in the context of the universe's origin remains one of the most profound and perplexing questions in cosmology. It pushes the boundaries of our knowledge and forces us to reconsider our fundamental assumptions about reality and existence. The concept of nothing has undergone a profound transformation in scientific understanding over the centuries. Ancient philosophers often equated nothing with a void or complete emptiness. However, modern physics has revealed that even in the seemingly empty vacuum of space, reality is far from devoid of activity. Quantum mechanics, a cornerstone of modern physics, tells us that the vacuum is actually teeming with energy and virtual particles. These particles constantly pop in and out of existence, their presence governed by the uncertainty principle. This quantum foam, as it is sometimes called, is a far cry from the classical notion of nothingness. In cosmology, the concept of nothing takes on even greater significance. Some theories suggest that our entire universe may have emerged from a quantum fluctuation in this vacuum state. This idea challenges our intuitive understanding of cause and effect, proposing that something as vast as our cosmos could arise from what we once considered nothing. Furthermore, the discovery of dark energy, which makes up about 68% of the universe, has added another layer to our understanding of nothing. This mysterious force, which drives the accelerating expansion of the universe, permeates what we once thought was empty space. It seems that in science, the more we learn about nothing, the more we realize it is actually something. The concept of true nothingness has puzzled philosophers and scientists for centuries. In our everyday experience, we often think of empty space as nothing, but even the vacuum of space is not truly empty. It contains quantum fluctuations, virtual particles that pop in and out of existence, and fields that permeate all of reality. From a scientific perspective, it is extremely difficult to create or observe true nothingness. Even in the most perfect vacuum we can create, quantum effects ensure that particles and energy are always present. The uncertainty principle in quantum mechanics suggests that true nothingness, devoid of all energy and matter, cannot exist for any measurable time. Some theories propose that the universe itself emerged from a state of nothingness through quantum fluctuations. However, this nothingness is not the absence of everything, but rather a state of pure potential from which our universe arose. This idea challenges our intuitive understanding of nothingness and existence. While true nothingness remains elusive in our physical reality, it continues to be an important theoretical concept in physics and philosophy. It serves as a baseline for understanding the nature of existence and the fundamental properties of our universe. The quest to understand nothingness drives scientific inquiry and pushes the boundaries of our knowledge about the fabric of reality. The concept of nothingness has intrigued philosophers, scientists, and thinkers across cultures for millennia. In Western philosophy, the ancient Greeks grappled with the idea of a void or non-being. Parmenides argued that nothingness could not exist, while atomists like Democritus proposed that the universe consisted of atoms moving through empty space. Eastern philosophies offer different perspectives on nothingness. In Buddhism, the concept of sunyata, or emptiness, is central, referring not to a nihilistic void, but to the absence of inherent existence in all phenomena. Taoism speaks of Wu, often translated as nothingness or non-being, which is seen as the source of all things and a state of potentiality. Modern physics has given us new ways to think about nothingness. Quantum field theory suggests that even in a vacuum devoid of matter, there is a sea of virtual particles popping in and out of existence. This quantum vacuum is far from empty, containing energy and potential for particle creation. The exploration of nothingness continues to fascinate scientists and philosophers alike. It challenges our understanding of existence, the nature of reality, and the very fabric of the universe. As we delve deeper into the mysteries of the cosmos, our conception of nothingness evolves, revealing a rich tapestry of ideas that span cultures, disciplines, and time. The concept of vacuum is crucial to our understanding of nothing in the universe. In everyday life, we might think of a vacuum as an empty space devoid of matter. However, in the realm of quantum physics, even the most perfect vacuum is far from empty. At the quantum level, a vacuum is teeming with activity. It is filled with fluctuating fields and virtual particles that constantly pop in and out of existence. These particles appear and disappear so quickly that they don't violate the conservation of energy. This phenomenon, known as quantum fluctuation, suggests that there is no such thing as true nothingness in our universe. The vacuum state is the lowest energy state of a quantum system, but it still contains a residual energy called zero-point energy. This energy is a fundamental property of space itself and cannot be removed. Some scientists speculate that this vacuum energy might be responsible for the expansion of the universe, acting as a form of dark energy. Understanding the nature of vacuum has profound implications for our comprehension of the universe's structure and evolution. It challenges our intuitive notions of emptiness and forces us to reconsider what we mean by nothing. The study of vacuum reveals that the fabric of space is intrinsically dynamic and complex, even in the absence of observable matter. Quantum mechanics revolutionizes our understanding of empty space, revealing it to be far from the featureless void we once imagined. In the quantum realm, empty space teems with activity, filled with virtual particles that constantly pop in and out of existence. These fleeting particles, existing for mere fractions of a second, arise from quantum fluctuations permitted by the uncertainty principle. This quantum foam, as it is sometimes called, challenges our classical notions of nothingness. Even in the absence of matter, the vacuum of space contains energy known as zero-point energy. This ever-present energy field permeates the universe, influencing the behavior of particles and potentially playing a role in the expansion of the cosmos. Quantum mechanics also introduces the concept of quantum fields that extend throughout space. These fields, such as the electromagnetic field, exist everywhere, even in regions we would classically consider empty. Particles themselves are viewed as excitations of these underlying fields, blurring the line between matter and empty space. Furthermore, quantum entanglement suggests that empty space might be more interconnected than we previously thought. Particles can be linked across vast distances, seeming to communicate instantaneously and defying our classical understanding of locality. This quantum interconnectedness hints at a deeper structure to the fabric of space itself, challenging our perception of emptiness and separation in the universe. The concept of nothing takes on distinct meanings in philosophy and physics, highlighting the complex nature of existence and reality. In philosophy, nothing often refers to the complete absence of anything, a state of non-existence that is difficult to comprehend. Philosophers have long debated whether true nothingness can exist or if it is merely a theoretical construct. Physics, on the other hand, approaches nothing from a more concrete perspective. In the realm of quantum mechanics, even the vacuum of space is not truly empty. Instead, it teems with virtual particles that constantly pop in and out of existence, creating a quantum foam of activity. This quantum vacuum state is the closest approximation to nothing that physicists can observe and study. The difference between these two interpretations of nothing reveals the gap between abstract thought and empirical observation. While philosophers grapple with the concept of absolute nothingness, physicists work within the framework of observable phenomena, where even the emptiest regions of space contain energy and potential. This distinction challenges our understanding of reality and raises questions about the nature of existence itself. As we continue to explore the universe, the interplay between philosophical and physical interpretations of nothing remains a fascinating area of inquiry, pushing the boundaries of human knowledge and understanding. Our understanding of nothingness has undergone a profound transformation as cosmology has advanced. In the past, people thought of nothing as a complete absence of everything, an empty void. However, modern physics has revealed that true nothingness is far more complex and intriguing than we ever imagined. Quantum mechanics, a cornerstone of modern physics, tells us that even in seemingly empty space, there is a constant flux of energy. This quantum vacuum is teeming with virtual particles that pop in and out of existence, borrowing energy from the vacuum itself. These fluctuations are so fundamental to the fabric of the universe that they cannot be eliminated, challenging our classical notion of nothingness. Cosmologists now consider the vacuum to be a dynamic entity, capable of expansion and potentially giving rise to entire universes. The inflationary theory of the early universe suggests that a small region of vacuum energy rapidly expanded, creating the cosmos we observe today. This implies that nothingness, far from being inert, might be the very wellspring of existence. Furthermore, the discovery of dark energy, which appears to permeate all of space and drive the accelerating expansion of the universe, adds another layer to our evolving concept of nothingness. What we once thought of as empty space is now understood to be filled with this mysterious energy, further blurring the line between something and nothing in the cosmos. Quantum fluctuations are tiny, rapid changes in energy that occur at the smallest scales of the universe. These fluctuations are a fundamental aspect of quantum mechanics, the branch of physics that describes the behavior of matter and energy at the atomic and subatomic levels. In the quantum world, the principle of uncertainty reigns supreme, allowing for brief moments where energy can appear and disappear seemingly out of nowhere. These fleeting energy variations happen constantly, even in what we consider to be empty space. In fact, what we once thought of as a perfect vacuum is actually teeming with activity at the quantum level. Particles and antiparticles pop into existence for incredibly short periods before annihilating each other, leaving no trace behind except for a subtle influence on the fabric of space-time itself. The importance of quantum fluctuations extends far beyond the realm of subatomic particles. Scientists believe these minute energy variations played a crucial role in the early universe, seeding the formation of cosmic structures we see today. During the inflationary period shortly after the Big Bang, quantum fluctuations were amplified to cosmic scales, creating slight irregularities in the distribution of matter and energy across the universe. These primordial fluctuations eventually led to the formation of galaxies, stars, and planets, shaping the cosmic landscape we observe today. Understanding quantum fluctuations not only helps us unravel the mysteries of the subatomic world, but also provides insights into the very origins and evolution of our vast universe. Quantum fluctuations play a crucial role in our understanding of the universe's origins. These tiny, unpredictable changes in energy levels occur constantly at the quantum scale, where the rules of classical physics break down. In the earliest moments of the universe, quantum fluctuations acted as seeds for the cosmic structure we observe today. During the inflationary period, mere fractions of a second after the Big Bang, the universe expanded at an incredible rate. This rapid expansion amplified quantum fluctuations, stretching them from subatomic scales to cosmic proportions. These fluctuations created slight variations in the density of matter and energy across the early universe. As the universe continued to expand and cool, these density variations became more pronounced. Areas with slightly higher density exerted stronger gravitational pull, attracting more matter over time. This process eventually led to the formation of galaxies, stars, and planets. Quantum fluctuations also help explain the slight temperature variations observed in the cosmic microwave background radiation, the afterglow of the Big Bang. These temperature differences, first detected by satellite observations, provide strong evidence for the quantum origins of cosmic structure and support our current models of the early universe. The Heisenberg uncertainty principle is a fundamental concept in quantum mechanics that reveals the inherent limitations of measuring certain pairs of physical properties simultaneously. Named after physicist Werner Heisenberg, this principle states that we cannot precisely determine both the position and momentum of a particle at the same time. The more accurately we measure one property, the less certain we become about the other. This uncertainty is not due to limitations in our measuring equipment, but rather a fundamental aspect of the quantum world. It reflects the wave-like nature of particles at the quantum scale, where they exist in a state of probability rather than definite values. The uncertainty principle plays a crucial role in understanding quantum fluctuations. These fluctuations are rapid changes in the amount of energy in a point in space, occurring on incredibly small scales. According to quantum field theory, even in seemingly empty space, particles and antiparticles are constantly popping into and out of existence. These fleeting particles, known as virtual particles, are a direct manifestation of the uncertainty principle. The connection between the uncertainty principle and quantum fluctuations lies in the relationship between energy and time. Just as we cannot precisely measure both position and momentum, we also cannot exactly determine both the energy of a system and the time at which it has that energy. This allows for brief violations of energy conservation, enabling the creation of virtual particles that quickly annihilate each other. These quantum fluctuations are believed to play a role in various phenomena, from the properties of the vacuum to the behavior of black holes, showcasing the strange and fascinating nature of the quantum realm. Quantum fluctuations are a fundamental aspect of our universe, occurring even in what we might consider absolute nothingness. In the realm of quantum mechanics, true emptiness does not exist. Instead, what we perceive as empty space is actually a sea of virtual particles constantly popping in and out of existence. These fleeting particles arise from the inherent uncertainty built into the fabric of the cosmos. According to the Heisenberg uncertainty principle, it is impossible to precisely measure both the position and momentum of a particle simultaneously. This uncertainty allows for brief violations of energy conservation, permitting particles to spontaneously appear and disappear. In the apparent vacuum of space, these quantum fluctuations create a background energy known as vacuum energy or zero-point energy. This energy is present everywhere, even in the coldest, most empty regions of the universe. It is a testament to the bizarre nature of quantum mechanics that even in the absence of matter, energy, or any observable phenomena, the quantum world remains active and dynamic. The concept of quantum fluctuations in nothingness challenges our classical understanding of reality and highlights the profound mysteries that still exist in our understanding of the universe. These fluctuations may have played a crucial role in the birth and evolution of our cosmos, potentially seeding the earlier structures that would eventually grow into the galaxies and clusters we observe today. Virtual particles play a crucial role in our understanding of quantum fluctuations, offering a glimpse into the bizarre and counterintuitive nature of the quantum world. These ephemeral particles constantly pop in and out of existence, emerging from the quantum vacuum for incredibly brief moments before annihilating each other. Quantum fluctuations occur due to the inherent uncertainty principle of quantum mechanics, which states that certain pairs of physical properties cannot be precisely determined simultaneously. This uncertainty allows for the temporary violation of energy conservation, enabling virtual particles to emerge from seemingly empty space. These fleeting particles have measurable effects on the physical world. For instance, they contribute to the Casimir effect, where two uncharged metal plates in a vacuum experience a tiny attractive force. Virtual particles also play a part in the decay of atomic nuclei and influence the properties of subatomic particles like electrons and quarks. By studying virtual particles and quantum fluctuations, scientists have gained deeper insights into the fundamental nature of reality. This knowledge has led to advancements in fields such as quantum field theory and has even provided clues about the early universe and the nature of dark energy. The concept of virtual particles reminds us that the quantum world is a realm of constant activity and uncertainty, challenging our classical notions of matter and energy. Quantum fluctuations, a fundamental aspect of quantum mechanics, have left their mark on the universe in ways we can observe today. One of the most compelling pieces of evidence comes from the cosmic microwave background radiation, the afterglow of the Big Bang. This ancient light shows tiny temperature variations that are believed to be the result of quantum fluctuations in the early universe, which were then amplified by cosmic inflation. In laboratory settings, scientists have observed the effects of quantum fluctuations through various experiments. The Casimir effect, for instance, demonstrates how quantum fluctuations can create a measurable force between two uncharged plates in a vacuum. This effect, predicted by Dutch physicist Hendrik Casimir in 1948, has been experimentally verified and provides strong support for the existence of quantum fluctuations. Another line of evidence comes from the study of virtual particles. According to quantum field theory, the vacuum is not truly empty, but filled with pairs of particles and antiparticles that constantly pop in and out of existence. While these virtual particles are typically too short-lived to observe directly, their effects can be measured. For example, they contribute to the Lamb shift, a small difference in the energy levels of hydrogen atoms that was unexplained by earlier quantum theories. The existence of Hawking radiation, theorized by Stephen Hawking, is also rooted in quantum fluctuations. Although not yet directly observed, this radiation is predicted to occur at the event horizons of black holes due to quantum effects. Ongoing research and technological advancements continue to provide new ways to detect and study quantum fluctuations, further solidifying their place in our understanding of the universe. Quantum fluctuations represent a fundamental departure from classical physics, revealing a universe that is inherently uncertain at its smallest scales. In the world of classical physics, objects have definite properties and follow predictable paths. But quantum fluctuations show us that at the quantum level, particles can spontaneously appear and disappear. Energy can briefly violate conservation laws, and the very fabric of space itself is in constant flux. These fluctuations arise from the Heisenberg uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot be precisely determined simultaneously. This inherent uncertainty leads to a constant churning of virtual particles popping in and out of existence, even in seemingly empty space. The implications of quantum fluctuations extend far beyond the microscopic realm. They play a crucial role in phenomena such as Hawking radiation from black holes, the Casimir effect between closely spaced materials, and even the large-scale structure of the universe. Some theories suggest that quantum fluctuations in the early universe were amplified by cosmic inflation, seeding the primordial density variations that eventually led to the formation of galaxies and clusters. By challenging our classical notions of determinism and continuity, quantum fluctuations force us to reconsider the nature of reality itself. They remind us that the universe is far stranger and more dynamic than our everyday experiences might suggest, operating on principles that often defy our intuition and push the boundaries of our understanding. Quantum fluctuations are fundamental to the quantum foam model of spacetime, a concept that challenges our understanding of the universe at its smallest scales. These fluctuations represent the constant creation and annihilation of virtual particles in the vacuum of space, occurring at incredibly tiny distances and for extremely brief moments of time. In the quantum foam model, these fluctuations cause spacetime to become turbulent and chaotic at the quantum scale, much like the frothy surface of a stormy sea. This foam-like structure is thought to exist at the Planck scale, which is about 1/quintillionth of the size of a proton. At this level, the smooth fabric of spacetime we experience in our everyday lives breaks down into a seething mass of quantum fluctuations. These quantum fluctuations are believed to give rise to microscopic wormholes and tiny black holes that pop in and out of existence in mere fractions of a second. This constant flux of virtual particles and spacetime distortions creates a dynamic, ever-changing landscape at the quantum level, challenging our classical notions of space and time. The quantum foam model, while still theoretical, has profound implications for our understanding of the universe. It suggests that at its most fundamental level, spacetime is not smooth and continuous, but granular and discrete. This concept could potentially help reconcile the seemingly incompatible theories of general relativity and quantum mechanics, bringing us closer to a unified theory of quantum gravity. The Big Bang Theory is our current best explanation for how the universe began. It proposes that approximately 13.8 billion years ago, all matter and energy in the cosmos was concentrated into an incredibly dense, hot state. This primordial singularity then rapidly expanded and cooled, setting the stage for the universe we observe today. In the first fractions of a second after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. This expansion caused the universe to grow from a size smaller than an atom to cosmic scales in an unimaginably brief moment. As the universe continued to expand and cool, it allowed for the formation of fundamental particles, then atoms, and eventually the large-scale structures we see today, such as galaxies and galaxy clusters. The Big Bang Theory is supported by several key pieces of evidence. One is the cosmic microwave background radiation, a faint glow of light that fills the entire sky, representing the afterglow of the Big Bang. Another is the observed expansion of the universe, with distant galaxies moving away from us at increasing speeds. The theory also accurately predicts the abundance of light elements like hydrogen and helium in the cosmos. It's important to note that the Big Bang Theory describes the rapid expansion of the universe from a hot, dense state, but it does not explain what caused this initial state or what came before it. These questions remain at the forefront of cosmological research, driving scientists to explore even deeper mysteries about the nature and origin of our universe. The Big Bang Theory was first proposed by Georges Lemaitre, a Belgian physicist and Roman Catholic priest, in the late 1920s. Lemaitre suggested that the universe began from a single primordial atom, which he called the cosmic egg, or the primeval atom. This idea laid the foundation for what would later become known as the Big Bang Theory. Lemaitre's groundbreaking concept was based on his interpretation of Einstein's theory of general relativity. He realized that the equations pointed to an expanding universe, which led him to the logical conclusion that if the universe is expanding, it must have had a beginning point in the distant past. Although Lemaitre proposed this idea in 1927, it did not gain immediate acceptance in the scientific community. It was only in the 1940s and 50s that the theory began to gather more support thanks to further theoretical work and observational evidence, such as the discovery of cosmic microwave background radiation in 1965. The term Big Bang itself was coined later, in 1949, by astronomer Fred Hoyle. Interestingly, Hoyle used the term somewhat derisively, as he was a proponent of the competing steady-state theory. Despite its initially mocking intent, the name stuck and is now universally used to describe the prevailing theory of the universe's origin. The Big Bang theory, our current best explanation for the origin of the universe, is supported by several key pieces of evidence. One of the most compelling is the cosmic microwave background radiation, a faint glow of light that fills the entire sky. This radiation is the afterglow of the Big Bang itself, cooled over billions of years as the universe expanded. Another crucial piece of evidence is the abundance of light elements in the universe. The Big Bang theory accurately predicts the amounts of hydrogen, helium, and lithium we observe in ancient stars and distant gas clouds. These ratios match what we would expect if these elements were forged in the intense heat of the early universe. The expansion of the universe also strongly supports the Big Bang theory. Observations of distant galaxies show they are moving away from us, and the farther away they are, the faster they're receding. This expansion is a natural consequence of a universe that began in an extremely hot, dense state and has been expanding ever since. Lastly, the distribution of galaxies across the cosmos aligns with predictions made by the Big Bang theory. Large-scale structures like galaxy clusters and cosmic voids form patterns that match what we would expect if the universe evolved from the tiny quantum fluctuations amplified by cosmic inflation in the earliest moments after the Big Bang. The Big Bang theory proposes that our universe began as an incredibly hot, dense point approximately 13.8 billion years ago. This initial state, often called a singularity, rapidly expanded and cooled, giving rise to the cosmos we observe today. However, it's crucial to understand that the Big Bang doesn't actually explain how the universe came from nothing. Instead, it describes the expansion and evolution of the universe from its earliest known state. The concept of the universe emerging from nothing is a complex philosophical and scientific question that goes beyond the scope of the Big Bang theory. Some theoretical physicists suggest that quantum fluctuations in a state of nothingness could potentially give rise to something, but these ideas remain highly speculative and unproven. What the Big Bang theory does explain is how the universe evolved from its initial hot, dense state. It accounts for the observed expansion of the universe, the cosmic microwave background radiation, and the abundance of light elements like hydrogen and helium. These predictions align remarkably well with astronomical observations, providing strong support for the theory. While the Big Bang is our best current explanation for the early universe, it leaves open questions about what came before and what caused the initial expansion. Scientists continue to explore these mysteries, pushing the boundaries of our understanding of the cosmos and its origins. Cosmic inflation is a crucial concept in modern cosmology that describes an incredibly rapid expansion of the early universe. This expansion occurred in the tiniest fraction of a second after the Big Bang, causing the universe to grow exponentially in size. The theory of cosmic inflation addresses several puzzling aspects of the Big Bang model. It explains why the universe appears so uniform on large scales and why it seems to be geometrically flat. Inflation also accounts for the origin of the cosmic structure we observe today, from galaxies to galaxy clusters. During the inflationary period, the universe expanded faster than the speed of light. This rapid growth stretched quantum fluctuations, which were present at the subatomic scale, into macroscopic variations in density. These variations later became the seeds for cosmic structure formation, leading to the galaxies and clusters we see today. cosmic inflation fits into the Big Bang model by occurring immediately after the initial singularity but before the formation of fundamental particles. It provides a bridge between the quantum realm of the earliest moments and the large-scale structure of the observable universe, offering a more complete picture of cosmic evolution. The Big Bang theory, while widely accepted, is not without its critics. One major criticism focuses on the concept of cosmic inflation, which suggests the universe expanded faster than light speed in its earliest moments. Some scientists argue this idea is difficult to test and potentially unfalsifiable. Another point of contention is the theory's reliance on dark matter and dark energy to explain certain observations. These mysterious components, which supposedly make up most of the universe, have yet to be directly detected, leading some to question their existence and the theory's validity. Critics also point to the horizon problem, which questions how the universe achieved its observed uniformity given the vast distances between regions that should not have been in causal contact. While inflation offers a potential solution, some find it unsatisfactory. Lastly, some scientists argue that the Big Bang theory does not adequately explain the origin of matter or the initial conditions of the universe. They contend that the theory describes the evolution of the universe but fails to address its ultimate beginning, leaving fundamental questions unanswered. The Big Bang theory has undergone significant refinement since its initial proposal by Georges Lemaitre in the 1920s. Originally conceived as the primeval atom hypothesis, it suggested the universe began from a single point of incredible density and heat. This idea gained traction when Edwin Hubble discovered that galaxies were moving away from us, indicating an expanding universe. As technology advanced, scientists uncovered new evidence supporting and reshaping the theory. The discovery of cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided crucial evidence for the Big Bang, as it represented the afterglow of the early universe. This finding led to the development of the hot Big Bang model, which became the standard cosmological paradigm. Further observations and theoretical work in the late 20th century led to the inclusion of cosmic inflation, a period of rapid expansion in the very early universe. This concept, proposed by Alan Guth, helped explain the uniformity of the cosmic microwave background and the flatness of space. It also provided a mechanism for the formation of large-scale structures in the universe. Today, the Big Bang theory incorporates dark matter and dark energy, mysterious components that make up most of the universe's mass and energy. These additions help explain observed phenomena like the accelerating expansion of the universe and the gravitational effects seen in galaxies and galaxy clusters. As new data emerges and our understanding grows, the Big Bang theory continues to evolve, remaining a cornerstone of modern cosmology while adapting to new discoveries. The cosmic microwave background radiation is the oldest light in the universe, a faint glow that fills all of space. This ancient radiation was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. This radiation provides strong evidence for the Big Bang theory. It represents the afterglow of the early universe, showing us a snapshot of the cosmos when it was just a fraction of its current age. The cosmic microwave background is remarkably uniform in all directions, which aligns with the idea that the universe expanded rapidly from an extremely hot, dense state. Scientists have mapped tiny temperature variations in this radiation, which correspond to areas of slightly different densities in the early universe. These variations are the seeds that eventually grew into the galaxies and large-scale structures we see today, further supporting the Big Bang model. The discovery of the cosmic microwave background was a watershed moment in cosmology. Its existence and properties match the predictions of the Big Bang theory so well that it has become one of the strongest pieces of evidence we have for how our universe began and evolved. Cosmic inflation is a pivotal concept in our understanding of the early universe. It describes an incredibly rapid expansion of space that occurred in the first fraction of a second after the Big Bang. During this brief period, the universe expanded faster than the speed of light, growing from a minuscule point to a vast expanse in an instant. This rapid expansion helps explain several puzzling features of our universe. It accounts for why the cosmos appears so uniform in all directions, even though distant regions should not have had time to interact. Inflation also explains why the universe is so flat, meaning parallel lines stay parallel over vast distances. Cosmic inflation solves the horizon and flatness problems that troubled earlier cosmological models. It predicts that tiny quantum fluctuations, present at the start of inflation, were stretched to cosmic scales. These fluctuations became the seeds for the formation of galaxies and large-scale structures we see today. While direct evidence for cosmic inflation remains elusive, its predictions align remarkably well with observations of the cosmic microwave background radiation. This ancient light, the afterglow of the Big Bang, shows patterns that strongly support the inflationary model, making it a cornerstone of modern cosmology. Alan Guth proposed the theory of cosmic inflation in 1980. He developed this groundbreaking idea to address several perplexing problems in cosmology that the standard Big Bang theory couldn't explain. One of the main issues Guth sought to resolve was the horizon problem. This puzzle concerns the remarkable uniformity of the cosmic microwave background radiation across the entire observable universe. According to the standard Big Bang model, regions of space that are far apart should never have been in causal contact, yet they show nearly identical temperatures. Inflation provides an elegant solution by suggesting that the entire observable universe originated from a minuscule region that was in causal contact before undergoing an exponential expansion. Inflation also offers an explanation for the flatness problem. Observations indicate that the universe is remarkably close to being spatially flat, which requires an incredibly precise initial density. Cosmic inflation naturally produces this flatness by stretching the universe to an enormous size, making any initial curvature virtually undetectable. Furthermore, the theory of cosmic inflation helps explain the origin of the large-scale structure we observe in the universe today. It proposes that quantum fluctuations existing at the subatomic scale were stretched to cosmic proportions during the inflationary period, seeding the formation of galaxies and galaxy clusters. Cosmic inflation addresses several key issues in the standard Big Bang model, providing a more comprehensive explanation for the early universe. This theory proposes that the universe underwent a period of rapid expansion in its first fraction of a second, growing exponentially in size. One major problem inflation solves is the horizon problem. In the standard model, distant regions of the universe should not have had time to interact and reach thermal equilibrium. Yet, we observe a remarkably uniform cosmic microwave background across the sky. Inflation explains this by suggesting that these regions were once in close contact before being rapidly stretched apart. Inflation also tackles the flatness problem. The universe appears to be extremely flat on large scales, which requires incredibly precise initial conditions in the standard model. However, inflation naturally produces this flatness by stretching any initial curvature to cosmic scales, much like inflating a balloon smooths out its surface. Furthermore, inflation provides a mechanism for the origin of cosmic structure. Quantum fluctuations, present during the inflationary period, would have been stretched to macroscopic scales, seeding the density variations that eventually led to the formation of galaxies and large-scale structures we see today. This elegant solution connects quantum mechanics with the largest structures in the universe, offering a more complete picture of cosmic evolution. The theory of cosmic inflation finds support in several key pieces of evidence. One of the most compelling is the remarkable uniformity of the cosmic microwave background radiation. This faint afterglow from the early universe shows an almost perfectly even temperature across the entire sky, suggesting that all regions of space were once in close contact, allowing them to reach thermal equilibrium. Another crucial piece of evidence is the flatness of space. Observations indicate that the universe is extraordinarily close to being geometrically flat, a condition that would be highly improbable without a period of rapid expansion. Inflation provides a natural explanation for this flatness by stretching out any initial curvature to nearly imperceptible levels. The theory also accounts for the absence of magnetic monopoles, which many theories predict should have been produced in abundance during the early universe. Inflation would have diluted these particles to such an extent that we would not expect to observe them today. Lastly, the distribution of galaxies and galaxy clusters in the universe aligns closely with predictions made by inflationary models. The slight variations in density that inflation would have amplified provide a good match for the large-scale structure we observe in the cosmos today. Cosmic inflation provides a compelling explanation for the remarkable uniformity we observe across vast distances in our universe. This theory proposes that in the earliest moments after the Big Bang, the universe underwent a period of exponential expansion, doubling in size roughly every 100 millionth of a trillionth of a trillionth of a second. This rapid growth stretched the fabric of space-time, smoothing out any initial irregularities and creating a vast, nearly uniform cosmic landscape. Before inflation, the observable universe was incredibly tiny, allowing for all regions to be in close contact and reach a state of thermal equilibrium. As inflation rapidly expanded this minuscule patch, it grew to encompass the entire observable universe we see today. This process essentially froze the uniformity achieved in that initial, compact state and spread it across cosmic scales. The uniformity we observe in the cosmic microwave background radiation, which shows temperature variations of only about 1 part in 100,000, is a direct consequence of this inflationary period. Without inflation, it would be difficult to explain how regions of space that appear to have never been in causal contact could exhibit such striking similarity in temperature and density. Inflation also explains why the universe appears flat on large scales. Just as blowing up a balloon smooths out its surface, the exponential expansion of space during inflation flattened any initial curvature, resulting in the nearly flat universe we observe today. This elegant solution to multiple cosmological puzzles has made inflation a cornerstone of modern Big Bang cosmology. The inflationary multiverse hypothesis proposes that our universe is just one of countless universes, all existing within an ever-expanding cosmic framework. This concept builds on the theory of cosmic inflation, which suggests that the early universe underwent a period of rapid expansion shortly after the Big Bang. According to this hypothesis, the process of inflation continues eternally in most regions of space. However, in some areas, inflation stops, leading to the formation of separate bubble universes. Our observable universe is thought to be one such bubble, while inflation continues beyond its boundaries, spawning new bubbles constantly. These bubble universes may have different physical laws, fundamental constants, and initial conditions. Some might be similar to ours, while others could be wildly different, perhaps unable to support the formation of stars, galaxies, or life as we know it. The inflationary multiverse hypothesis offers potential explanations for some perplexing aspects of our universe, such as its apparent fine-tuning for life. It suggests that with an infinite number of universes, the existence of one like ours becomes not only possible, but inevitable. However, this hypothesis remains speculative and challenging to test empirically, as other universes would lie beyond our observable cosmic horizon. Cosmic inflation and eternal inflation are closely connected theories that shed light on the early moments and potential structure of our universe. Cosmic inflation proposes that the universe underwent a period of rapid expansion in its first fraction of a second, growing exponentially in size. This expansion smoothed out irregularities and set the stage for the universe we observe today. Eternal inflation takes this concept further, suggesting that the inflationary phase of the universe's expansion never fully ends. Instead, it continues indefinitely in some regions while stopping in others. This creates a scenario where new universes or bubble universes are constantly forming within an ever-expanding cosmic framework. In this model, our observable universe is just one of countless bubbles in a vast, eternally inflating multiverse. Each bubble universe might have its own unique properties, physical laws, and conditions. The regions between these bubbles continue to expand at an accelerated rate, providing space for more bubble universes to form. The relationship between cosmic inflation and eternal inflation highlights the potential for a much larger and more diverse cosmos than we can directly observe. It challenges our understanding of the universe's beginning and raises intriguing questions about the nature of reality and the possibility of other universes beyond our own. Dark energy and cosmic inflation are both crucial concepts in our understanding of the universe's evolution, though they operate at different times and scales. Cosmic inflation is theorized to have occurred in the first fraction of a second after the Big Bang, causing the universe to expand at an incredible rate. Dark energy, on the other hand, is believed to be responsible for the accelerating expansion of the universe we observe today. While cosmic inflation was an extremely rapid expansion in the early universe, dark energy is causing a much slower acceleration of expansion in the present day. The connection between these two phenomena lies in their similar effects on space-time, as both cause the fabric of the universe to stretch. Some scientists have proposed that dark energy and the force behind cosmic inflation might be related or even manifestations of the same underlying phenomenon. However, this connection remains speculative, and more research is needed to fully understand the relationship between these two cosmic forces. Interestingly, the study of dark energy has led to refinements in inflationary models, helping cosmologists better understand the conditions of the early universe and how they relate to what we observe today. As our knowledge of both dark energy and cosmic inflation continues to grow, we may uncover deeper connections between these fundamental aspects of our universe. String theory is a fascinating concept in theoretical physics that attempts to unify our understanding of the universe's fundamental forces and particles. At its core, string theory proposes that all matter and energy in the universe are composed of incredibly tiny, vibrating strings of energy. These strings are so small that if an atom were the size of our solar system, a string would be no larger than a tree on Earth. According to string theory, the different vibrations of these strings give rise to all the particles and forces we observe in nature. Just as a guitar string can produce different musical notes when plucked, these cosmic strings can vibrate in various ways, creating the diverse array of particles that make up our reality. This includes familiar particles like electrons and quarks, as well as more exotic entities like gravitons, the hypothetical particles that carry the force of gravity. One of the most intriguing aspects of string theory is its suggestion that our universe may have more dimensions than the 4 we experience in everyday life: 3 spatial dimensions and 1 of time. String theory proposes that there could be 10, 11, or even more dimensions, most of which are curled up so tightly that we cannot perceive them directly. These extra dimensions could potentially explain some of the mysteries that have long puzzled physicists, such as the weakness of gravity compared to other fundamental forces. While string theory offers an elegant and potentially unifying framework for understanding the universe, it remains highly speculative. Scientists have yet to find experimental evidence to support its predictions, and some critics argue that it may be impossible to test conclusively. Despite these challenges, string theory continues to captivate physicists and cosmologists, driving ongoing research and inspiring new ways of thinking about the nature of reality itself. String theory proposes a radical reimagining of the fundamental nature of our universe. At its core, this theory suggests that the basic building blocks of reality are not point-like particles, but incredibly tiny, vibrating strings of energy. These strings, far smaller than even the smallest subatomic particles we can currently detect, are thought to vibrate in different ways, giving rise to all the particles and forces we observe in the cosmos. In the context of the universe's origin, string theory offers a compelling framework. It suggests that our universe might have emerged from a collision or interaction between vast, multidimensional membranes, often called branes. This cosmic collision could have released an enormous amount of energy, triggering the expansion and evolution of our universe in what we commonly refer to as the Big Bang. String theory also introduces the concept of extra dimensions beyond the four we experience in our daily lives. These additional dimensions, tightly curled up and hidden from our direct perception, could explain why gravity appears so much weaker than the other fundamental forces. The theory proposes that gravity might be just as strong as the other forces, but most of its effects are spread out across these extra dimensions. By providing a unified description of all particles and forces, including gravity, string theory attempts to bridge the gap between quantum mechanics and general relativity. This unification could potentially offer insights into the earliest moments of the universe, a time when quantum effects and gravitational forces were both extremely significant. While string theory remains highly speculative and lacks experimental evidence, it continues to intrigue scientists as a possible path toward a deeper understanding of our cosmic origins. String theory proposes that our universe contains additional spatial dimensions beyond the three we can observe. These extra dimensions are thought to be tightly curled up and incredibly small, existing at scales far tinier than even subatomic particles. Most versions of string theory suggest there are 6 or 7 of these extra dimensions, bringing the total number of spatial dimensions to 9 or 10 when combined with our familiar 3. These extra dimensions are not just empty space, but are believed to have complex shapes and structures called Calabi-Yau manifolds. The exact configuration of these hidden dimensions could explain many of the fundamental properties of our universe, including the types of particles that exist and the forces that govern their interactions. The concept of extra dimensions helps resolve some of the contradictions between quantum mechanics and general relativity. It allows for the unification of all fundamental forces, including gravity, into a single, coherent framework. In this view, the particles we observe are actually tiny vibrating strings, and the different vibration patterns of these strings in the extra dimensions give rise to the diverse particles and forces we see in our three-dimensional world. While these extra dimensions remain purely theoretical and have not been directly observed, scientists continue to search for indirect evidence of their existence through experiments at particle accelerators and observations of cosmic phenomena. The idea of hidden dimensions challenges our perception of reality and opens up new possibilities for understanding the fundamental nature of our universe. The concept of multiple dimensions offers intriguing possibilities for explaining the origin and nature of our universe. Beyond the 3 spatial dimensions and 1 time dimension we experience, scientists theorize that additional dimensions could exist, hidden from our direct perception. These extra dimensions might play a crucial role in the creation and structure of our cosmos. String theory, a prominent framework in theoretical physics, suggests that our universe could be a 3-dimensional membrane floating in a higher dimensional space. This higher dimensional realm, often called the bulk, might contain other universes, each with its own set of physical laws. The interaction between these dimensions could have triggered the birth of our universe. Some models propose that the collision of 2 membranes in the bulk sparked the Big Bang, releasing the enormous energy that formed our cosmos. Alternatively, the extra dimensions might explain the weakness of gravity compared to other fundamental forces, as its effects could be spread across multiple dimensions. Understanding these additional dimensions could potentially resolve long-standing puzzles in physics, such as the nature of dark matter and dark energy. However, detecting and proving the existence of extra dimensions remains a significant challenge for scientists, requiring advanced technology and innovative experimental approaches. M-theory represents a unifying framework in theoretical physics that aims to reconcile various versions of string theory. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings of energy. M-theory takes this concept further, suggesting that these strings exist in 11 dimensions rather than the 10 dimensions proposed by earlier string theories. The M in M-theory has been interpreted in various ways, including membrane, matrix, or mystery. This theory posits that our universe might be a large membrane floating in a higher dimensional space alongside other membrane universes. These membranes, or branes, can interact with each other, potentially explaining phenomena like gravity and the creation of our universe. M-theory provides a more comprehensive picture than individual string theories by showing how they can be different aspects of the same underlying theory. It suggests that what appeared to be distinct string theories are actually different ways of looking at the same thing, much like how a three-dimensional object can cast different two-dimensional shadows depending on the angle of light. While M-theory offers exciting possibilities for understanding the fundamental nature of reality, it remains highly speculative and challenging to test experimentally. Scientists continue to work on developing ways to verify its predictions and explore its implications for our understanding of the cosmos. String theory offers a potential solution to one of the most perplexing challenges in modern physics, unifying quantum mechanics and general relativity. These two fundamental theories have long been at odds, describing the universe in seemingly incompatible ways. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity explains gravity and the structure of spacetime on cosmic scales. At its core, string theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings are so small that they appear as particles to our current instruments. The different vibrations of these strings give rise to all the particles and forces we observe in nature, including gravity. By reimagining particles as strings, the theory provides a framework that can potentially describe both quantum phenomena and gravitational effects consistently. In the string theory model, gravity emerges naturally as a consequence of the string's vibrations, rather than being a separate force that needs to be reconciled with quantum mechanics. Moreover, string theory requires the existence of extra dimensions beyond the four we experience in everyday life. These additional dimensions, while hidden from our direct perception, play a crucial role in how the strings vibrate and interact, potentially explaining the complex behavior we observe in both quantum and relativistic realms. This unification of quantum mechanics and general relativity within a single theoretical framework represents a significant step toward a comprehensive understanding of the universe at all scales. The concept of extra dimensions beyond the four we experience daily, three spatial dimensions and time, has intrigued physicists for decades. While direct observation remains elusive, several lines of evidence and theoretical frameworks support the possibility of their existence. String theory, a prominent candidate for a unified theory of physics, proposes that our universe consists of 10 or 11 dimensions. This theory elegantly resolves many inconsistencies between quantum mechanics and general relativity, but only if these extra dimensions exist. Certain unexplained phenomena in particle physics hint at the potential presence of extra dimensions. For instance, the weakness of gravity compared to other fundamental forces could be explained if gravity operates across additional dimensions, effectively diluting its strength in our observable universe. Experiments at particle accelerators like the Large Hadron Collider search for signs of extra dimensions. Scientists look for missing energy in particle collisions or the creation of microscopic black holes, which would indicate the presence of hidden dimensions. While no conclusive evidence has been found yet, these ongoing experiments continue to probe the boundaries of our understanding and may one day reveal the existence of a higher dimensional reality. String theory offers a fascinating potential explanation for the apparent fine-tuning of our universe. This complex framework proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings of energy. These strings vibrate in different ways, giving rise to all the particles and forces we observe in nature. One of the most intriguing aspects of string theory is its prediction of multiple dimensions beyond the four we experience in everyday life. According to some versions of the theory, our universe might be just one of many existing in a vast multiverse. Each universe in this multiverse could have different physical laws and constants, determined by how the extra dimensions are compactified or curled up. This multiverse concept provides a possible solution to the fine-tuning problem. Instead of our universe being uniquely designed with precise parameters that allow for complex structures and life, it might be one of countless universes with varying conditions. In this scenario, we naturally find ourselves in a universe compatible with our existence, while many others remain inhospitable or unable to support complex structures. String theory thus suggests that what appears to be fine-tuning might actually be a selection effect. We observe a universe that seems perfectly suited for life because we could only exist in such a universe. This idea, known as the anthropic principle, shifts our perspective from seeing our universe as uniquely designed to viewing it as one of many possible configurations in a much larger cosmic landscape. Quantum cosmology is a fascinating field that combines the principles of quantum mechanics with the study of the entire universe. It seeks to explain the very early stages of our cosmos, particularly the first fraction of a second after the Big Bang, when the universe was incredibly small and dense. In this realm, the laws of quantum physics, which govern the behavior of subatomic particles, become crucial in understanding how the universe began and evolved. Quantum cosmology attempts to reconcile the microscopic world of quantum mechanics with the macroscopic world of general relativity, providing a more complete picture of cosmic evolution. One of the key concepts in quantum cosmology is the idea of a wave function for the entire universe. This mathematical construct describes the quantum state of the cosmos, encompassing all possible configurations and outcomes. Scientists use this framework to explore how quantum fluctuations in the early universe might have given rise to the large-scale structures we observe today, such as galaxies and galaxy clusters. Quantum cosmology also grapples with profound questions about the nature of time, space, and the multiverse. It suggests that our universe might be just one of many possible universes, each with its own set of physical laws and constants. This field continues to push the boundaries of our understanding, challenging our perceptions of reality and our place in the cosmos. Quantum cosmology and classical cosmology represent two distinct approaches to understanding the universe, each operating on different scales and principles. Classical cosmology deals with the large-scale structure and evolution of the universe, relying on Einstein's theory of general relativity. It explains phenomena like the expansion of the universe, the formation of galaxies, and the cosmic microwave background radiation. In contrast, quantum cosmology attempts to apply the principles of quantum mechanics to the entire universe. This approach becomes crucial when examining the earliest moments of the universe, particularly the Planck era, occurring mere fractions of a second after the Big Bang. During this period, the universe was so small and dense that quantum effects dominated, making classical physics inadequate for describing its behavior. Quantum cosmology seeks to reconcile general relativity with quantum mechanics, addressing fundamental questions about the origin and nature of the universe. It explores concepts like the wave function of the universe and the possibility of multiple universes or a multiverse. This field also grapples with the problem of time, as the notion of time itself becomes ambiguous at the quantum scale. While classical cosmology provides a robust framework for understanding the observable universe, quantum cosmology delves into the realm of the extremely small and the extremely early, offering potential insights into the very foundations of reality. Both approaches are essential for a comprehensive understanding of our cosmos, from its smallest constituents to its largest structures. The Wheeler-DeWitt equation is a fundamental concept in quantum cosmology, attempting to merge quantum mechanics with general relativity. Named after physicists John Wheeler and Bryce DeWitt, this equation aims to describe the behavior of the entire universe as a quantum system. At its core, the Wheeler-DeWitt equation suggests that the universe as a whole does not evolve with time in the same way that objects within it do. Instead, it proposes that the universe exists in a timeless state, with all possible configurations coexisting simultaneously. This idea challenges our conventional understanding of time and the origin of the universe. One of the most intriguing implications of the Wheeler-DeWitt equation is its perspective on the Big Bang. Rather than viewing the Big Bang as the absolute beginning of the universe, this equation hints at the possibility that our universe might be part of a larger, timeless structure. It suggests that the apparent beginning of time could be an emergent property rather than a fundamental aspect of reality. However, the Wheeler-DeWitt equation remains highly theoretical and controversial. While it offers fascinating insights into the nature of the cosmos, scientists continue to grapple with its implications and seek ways to test its predictions experimentally. As our understanding of quantum gravity advances, the Wheeler-DeWitt equation may play a crucial role in unraveling the deepest mysteries of our universe's origin and structure. Quantum cosmology tackles the challenge of understanding the universe's earliest moments by merging quantum mechanics with theories of gravity. This approach becomes crucial when we consider that in its infancy, the universe was incredibly small and dense, a realm where quantum effects dominate. At these minuscule scales, traditional models of gravity break down, and we need a new framework to describe how space and time behave. Quantum cosmology proposes that the universe itself might have emerged from quantum fluctuations, much like particles popping in and out of existence in the quantum vacuum. One key concept in quantum cosmology is the wave function of the universe, which describes all possible states the cosmos could have. This idea suggests that our universe might be just one realization out of many potential outcomes, each with different physical laws and constants. Quantum cosmology also grapples with the notion of time at the universe's birth. Some theories propose that time as we understand it might not have existed in the earliest moments, emerging only as the universe expanded and cooled. This perspective challenges our conventional understanding of cause and effect at the dawn of existence. Wave functions play a crucial role in quantum cosmology, serving as the fundamental mathematical tools used to describe the quantum state of the universe. In this context, they represent the probability distribution of various possible configurations of the cosmos at its earliest stages. Unlike classical physics, where we can precisely determine the position and momentum of objects, quantum cosmology deals with probabilities and uncertainties. The wave function of the universe encapsulates all potential states it could exist in, allowing cosmologists to model how different cosmic configurations might have evolved from the quantum realm to the large-scale structures we observe today. These wave functions are solutions to the Wheeler-DeWitt equation, which is essentially the Schrödinger equation applied to the entire universe. They provide a framework for understanding how quantum fluctuations in the early universe could have given rise to the cosmic microwave background radiation and the seeds of galaxy formation. By studying these wave functions, scientists aim to bridge the gap between quantum mechanics and general relativity, potentially offering insights into the nature of time, the origin of the universe, and the fundamental laws that govern cosmic evolution. This approach brings us closer to understanding the quantum nature of gravity and the very fabric of space-time itself. Quantum cosmology tackles the perplexing issue of time in the early universe by merging quantum mechanics with theories of gravity. This approach becomes crucial when we consider the extreme conditions present during the universe's earliest moments, where classical physics breaks down and quantum effects dominate. In the realm of quantum cosmology, time as we understand it becomes fuzzy and loses its definitive nature. Instead of a smooth, continuous flow, time might be better described as discrete units or quantum leaps. This concept challenges our everyday perception of time and suggests that in the nascent universe, the distinction between past, present, and future might have been meaningless. One key idea in quantum cosmology is the Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe. Intriguingly, this equation does not contain time as a parameter, leading to what physicists call the problem of time. This absence of time in the fundamental equation raises profound questions about how our familiar notion of time emerges from this timeless quantum state. Some theories propose that time as we know it only emerged as the universe expanded and cooled, transitioning from a purely quantum state to one where classical physics applies. This emergence of time is linked to the process of decoherence, where quantum superpositions collapse into definite states, potentially giving rise to the arrow of time we experience. By exploring these concepts, quantum cosmology offers a framework to understand the nature of time itself and how it came to be in our expanding universe. Quantum cosmology grapples with some of the most profound questions in physics, seeking to unite quantum mechanics with our understanding of the universe at its largest scales. One major challenge lies in reconciling the probabilistic nature of quantum mechanics with the deterministic behavior we observe in the cosmos. Scientists struggle to apply quantum principles to the entire universe, as our current theories break down when describing the extreme conditions of the early universe. Another significant hurdle is the lack of observational evidence. The quantum effects that dominated the universe in its earliest moments are incredibly difficult to detect or replicate today. This leaves researchers with limited data to test their theories, forcing them to rely heavily on mathematical models and theoretical predictions. The problem of time presents yet another obstacle. In quantum mechanics, time is treated as a background parameter, while in general relativity, it becomes a dynamic variable. Reconciling these conflicting views of time in a unified theory of quantum gravity remains a formidable challenge for physicists. Lastly, the multiverse hypothesis, which emerges from some quantum cosmological models, raises philosophical and scientific questions about the nature of reality and the limits of our ability to test and verify theories beyond our observable universe. These challenges continue to push the boundaries of our understanding and drive ongoing research in the field of quantum cosmology. Quantum cosmology offers a fascinating approach to addressing the long-standing problem of the initial singularity in our understanding of the universe's origins. This field combines the principles of quantum mechanics with theories of gravity to explore the earliest moments of cosmic history. Traditional models of the Big Bang suggest that the universe began from an infinitely dense point, a singularity where the laws of physics as we know them break down. However, quantum cosmology proposes that quantum effects become significant at extremely small scales and high energies, potentially eliminating the need for a singular beginning. One key idea in quantum cosmology is the concept of a quantum foam, where space and time become fuzzy and indeterminate at the smallest scales. In this scenario, the universe might have emerged from quantum fluctuations in this foam, avoiding the problem of infinite density altogether. Some theories even suggest that the universe could have tunneled into existence from a pre-existing state, similar to how particles can quantum tunnel through barriers. Another intriguing possibility is the idea of a bouncing universe, where the cosmos contracts to a small but finite size before expanding again. Quantum effects could prevent the universe from reaching a true singularity, instead causing it to rebound in a new phase of expansion. This concept challenges the notion of a single, definitive beginning and opens up the possibility of a cyclical or oscillating universe. The multiverse theory proposes that our universe is not alone, but part of a vast collection of universes, each with its own unique properties and physical laws. This concept challenges our traditional understanding of reality and suggests that what we perceive as the entirety of existence is just a small fraction of a much larger cosmic landscape. According to this theory, these multiple universes might exist in parallel, branching off from one another, or even occupying different dimensions. Some versions of the multiverse theory suggest that every possible outcome of events occurs somewhere across these infinite universes, creating an endless array of alternate realities. Scientists have proposed several types of multiverses, including the quantum multiverse, where new universes are created with each quantum event, and the inflationary multiverse, where rapid expansion after the Big Bang led to the formation of separate bubble universes. Another intriguing possibility is the brain multiverse, where universes exist as membranes floating in higher dimensional space. While the multiverse theory remains highly speculative and currently unprovable, it has captured the imagination of physicists and cosmologists worldwide. It offers potential explanations for some of the most perplexing questions in physics, such as the fine-tuning of universal constants and the nature of quantum mechanics. As our understanding of the cosmos continues to evolve, the multiverse theory remains a fascinating frontier of scientific exploration. The multiverse theory proposes that our universe is not alone, but part of a vast ensemble of universes, each with its own unique properties and laws of physics. This concept directly challenges the idea of a single, special creation event for our cosmos. In the context of universal origins, the multiverse theory suggests that universes are continually being born through various mechanisms. One popular model posits that universes bubble up from a primordial quantum foam, expanding rapidly much like our own Big Bang. Another perspective, derived from string theory, envisions our universe as one of many parallel worlds existing on different dimensional branes. These ideas reshape our understanding of cosmic creation. Instead of a lone universe springing into existence, we might be part of an endless cycle of universe formation. This view potentially solves puzzles about our universe fine-tuning, as in a multiverse, universes with different physical constants would naturally arise, and only those suitable for life would be observed. However, it is crucial to note that while the multiverse theory is compelling, it remains speculative. The challenge lies in gathering empirical evidence, as other universes, by definition, lie beyond our observable realm. Despite this, the concept continues to intrigue cosmologists and reshape our perspective on the nature of existence and the cosmos at large. Scientists have proposed several intriguing types of multiverses, each offering a unique perspective on the nature of reality beyond our observable universe. The most widely discussed is the inflationary multiverse, which suggests that our universe is just one of many bubbles that formed during the rapid expansion of space in the early moments after the Big Bang. These bubble universes might have different physical laws and constants, creating a vast array of cosmic possibilities. Another fascinating concept is the quantum multiverse, based on the many worlds interpretation of quantum mechanics. This theory proposes that every possible outcome of a quantum event occurs, each in its own separate universe. This leads to an almost unimaginable number of parallel realities branching off at every moment. String theory, a candidate for a unified theory of physics, gives rise to the idea of a brain multiverse. In this model, our universe exists on a three-dimensional membrane or brane floating in a higher dimensional space. Other branes might exist parallel to ours, potentially with their own unique properties and physical laws. Lastly, the cyclic multiverse suggests that our universe is just one in an endless cycle of big bangs and big crunches, with each cycle giving birth to a new universe. This concept challenges our understanding of time and the origins of the cosmos, proposing that our universe might be just one iteration in an eternal cosmic dance. Eternal inflation provides a compelling framework that bolsters the idea of a multiverse. This theory suggests that our universe is just one of countless bubbles in an ever-expanding cosmic foam. As space expands at an exponential rate, quantum fluctuations cause some regions to stop inflating and form distinct universes, while inflation continues elsewhere. The key to eternal inflation lies in its never-ending nature. While some areas cease inflating and become separate universes like our own, the space between these bubbles continues to expand rapidly. This ongoing process generates new regions that can spawn additional universes, potentially with different physical laws and constants. This mechanism naturally leads to the concept of a multiverse, as it provides a way for numerous universes to come into existence. Each of these bubble universes could have unique properties, from subtle variations in the strength of fundamental forces to radically different forms of matter and energy. The eternal inflation model thus offers a scientific basis for the existence of multiple universes, transforming the multiverse from a purely philosophical concept into a testable hypothesis. While direct observation of other universes remains beyond our current capabilities, the theory of eternal inflation continues to intrigue cosmologists as they seek to understand the ultimate nature of reality. The anthropic principle is a philosophical concept that attempts to explain why our universe appears to be finely tuned for the existence of life. It suggests that the fundamental constants and laws of physics we observe are precisely what they need to be for intelligent observers like us to exist and ponder the nature of the cosmos. This principle relates to the multiverse theory in a fascinating way. The multiverse hypothesis proposes that our universe is just one of many, possibly infinite, universes existing simultaneously. Each of these universes might have different physical laws, constants, and initial conditions. In this context, the anthropic principle suggests that we find ourselves in a universe compatible with our existence simply because we could not exist in universes with different parameters. The multiverse offers a potential explanation for the apparent fine-tuning of our universe without resorting to the idea of a deliberate design. If there are countless universes with varying properties, it becomes statistically likely that at least one of them would have the right conditions for life to emerge. We happen to inhabit that universe because it is the only one in which we could exist to make such observations. Critics argue that the multiverse theory is untestable and therefore unscientific. However, proponents suggest that it provides a logical framework for understanding our place in the cosmos and why our universe seems so improbably hospitable to life. The interplay between the anthropic principle and the multiverse continues to be a topic of intense debate and research in cosmology and philosophy of science. The concept of multiple universes, often called the multiverse, is a fascinating idea that has captured the imagination of scientists and the public alike. While we cannot directly observe other universes, several lines of scientific reasoning suggest their possible existence. Quantum mechanics, the theory describing the behavior of matter at the smallest scales, provides one intriguing avenue of support. The many worlds interpretation of quantum mechanics proposes that every time a quantum event occurs, the universe splits into multiple versions, each representing a different outcome. This interpretation, while controversial, aligns with the mathematical framework of quantum theory. String theory, a theoretical framework in physics, also hints at the possibility of multiple universes. According to some versions of string theory, our universe might be just one of many universes existing as membranes in higher dimensional space. These universes could potentially interact with each other, leaving subtle imprints that scientists are searching for in the cosmic microwave background radiation. Cosmological observations offer another potential source of evidence. The inflationary model of the early universe suggests that space underwent a period of rapid expansion shortly after the Big Bang. Some scientists propose that this process could create multiple bubble universes, each with its own physical laws and constants. While we cannot observe these other universes directly, the theory makes predictions about the properties of our own universe that scientists continue to test and refine. The multiverse theory proposes that our universe is not alone, but part of a vast ensemble of universes, each with its own unique properties and laws of physics. This concept fundamentally alters our perception of reality by suggesting that what we consider to be the entirety of existence is merely a small fraction of a much grander cosmic landscape. One of the most profound implications of the multiverse theory is that it challenges the notion of uniqueness in our universe. The constants and laws that govern our reality might be just one set among countless possibilities. This idea raises questions about the apparent fine-tuning of our universe for life, as the existence of multiple universes could explain why ours seems so perfectly suited for our existence. The multiverse theory also has implications for our understanding of causality and the nature of physical laws. In a multiverse scenario, events that seem impossible in our universe might be commonplace in others, blurring the lines between what we consider possible and impossible. This concept forces us to reconsider the fundamental nature of reality itself and the limits of our scientific understanding. Furthermore, the multiverse theory challenges our notions of cosmic significance. If our universe is one of many, it raises questions about our place in the grand scheme of existence and whether the concept of purpose or meaning extends beyond the boundaries of our own universe. This shift in perspective invites us to contemplate the true scale of reality and our role within it. The multiverse theory challenges our fundamental understanding of reality and existence. This concept suggests that our universe is just one of many, perhaps infinite universes existing simultaneously. Each of these universes might have different physical laws, constants, or even different versions of ourselves. This theory has profound implications for our place in the cosmos. If true, it would mean that our universe, despite its vastness, is just a tiny fraction of all that exists. It raises questions about the uniqueness of our existence and the nature of possibility itself. In a multiverse, everything that can happen may indeed happen in some universe, blurring the lines between potential and actuality. The multiverse also impacts our understanding of fine-tuning in the universe. The apparent perfect conditions for life in our universe could be explained not by design, but by the sheer number of universes with different conditions. This shifts the philosophical debate around the anthropic principle and the origins of our universe-friendly physical constants. Moreover, the multiverse concept challenges our notions of choice and free will. If all possible outcomes occur in different universes, it raises questions about the nature of decision-making and personal responsibility. These philosophical quandaries demonstrate how the multiverse theory extends far beyond physics, touching on core aspects of human existence and our understanding of reality itself. Vacuum energy is a fundamental concept in quantum physics that challenges our everyday understanding of empty space. Far from being a void, the vacuum of space is actually teeming with activity at the subatomic level. This energy permeates every corner of the universe, existing even in the absence of matter and radiation. At its core, vacuum energy arises from the constant creation and annihilation of virtual particles. These particles pop into existence and disappear almost instantaneously, their fleeting presence a consequence of the uncertainty principle in quantum mechanics. This ceaseless dance of particles coming in and out of being generates a background energy that persists throughout space. The implications of vacuum energy extend far beyond the realm of particle physics. Some scientists propose that it might play a role in the expansion of the universe, potentially contributing to dark energy, the mysterious force driving cosmic acceleration. However, there is a significant discrepancy between theoretical predictions of vacuum energy's strength and astronomical observations, a puzzle known as the cosmological constant problem. Understanding vacuum energy is crucial for our comprehension of the universe's fundamental nature. It challenges our notions of emptiness and forces us to reconsider the very fabric of space itself. As we continue to probe the mysteries of the cosmos, vacuum energy remains a captivating and enigmatic subject, promising further insights into the workings of our universe. Vacuum energy challenges our intuitive understanding of nothingness. In everyday life, we think of a vacuum as empty space devoid of matter. However, quantum physics reveals that even in the absence of particles, the vacuum is far from empty. At the quantum level, the vacuum is a seething cauldron of activity. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum itself. These fleeting particles, existing for mere fractions of a second, contribute to what we call vacuum energy. This energy permeates all of space, even in regions we might consider completely empty. It's a fundamental property of the universe, representing the lowest possible energy state of any given region. Remarkably, this energy of nothing may play a crucial role in cosmic processes, potentially influencing the expansion of the universe. The presence of vacuum energy forces us to reconsider our notion of nothingness. It suggests that true emptiness, completely devoid of energy or potential, might not exist in our universe. Even in the depths of intergalactic space, far from any visible matter, this underlying energy persists, reminding us that the cosmos is never truly empty. Zero-point energy is a fundamental concept in quantum physics that challenges our everyday understanding of emptiness. Even in the most perfect vacuum, devoid of all matter, energy continues to exist at its lowest possible level. This energy, ever present and unavoidable, is what we call zero-point energy. At the quantum scale, the vacuum is far from empty. It teems with activity as virtual particles constantly pop in and out of existence, their fleeting presence a result of quantum fluctuations. These fluctuations are rooted in the Heisenberg uncertainty principle, which states that we cannot simultaneously know both the position and momentum of a particle with absolute precision. The consequences of zero-point energy extend beyond the realm of the infinitesimally small. Some scientists speculate that it might play a role in cosmic expansion, potentially contributing to the mysterious dark energy that seems to be accelerating the universe's growth. However, reconciling the observed cosmic expansion with theoretical predictions of zero-point energy remains a significant challenge in modern physics. Understanding zero-point energy not only pushes the boundaries of our knowledge about the nature of reality, but also raises intriguing possibilities for future technologies. While harnessing this energy remains in the realm of speculation, its existence reminds us that the universe is far more complex and mysterious than it might appear at first glance. Vacuum energy, also known as zero-point energy, is a fundamental concept in quantum physics that may have played a crucial role in the birth of our universe. This energy exists everywhere, even in the seemingly empty space between particles. In the earliest moments of the universe, vacuum energy could have acted as a driving force behind cosmic inflation, the rapid expansion that occurred just after the Big Bang. During this inflationary period, the universe expanded at an incredible rate, doubling in size many times over in a fraction of a second. This expansion was powered by the repulsive nature of vacuum energy, which pushed space itself apart. As the universe expanded, it cooled, allowing matter and energy to condense into the forms we see today. The concept of vacuum energy also ties into the idea of quantum fluctuations. These microscopic variations in energy levels may have been amplified during inflation, leading to the formation of the cosmic structures we observe today, such as galaxies and galaxy clusters. The seeds of our cosmic landscape may have been sown by the quantum nature of vacuum energy. While the exact mechanisms are still debated among cosmologists, the role of vacuum energy in the universe's creation highlights the profound connection between the quantum world and the largest scales of our cosmos. It reminds us that even the vast emptiness of space is teeming with hidden energy, shaping the very fabric of our reality. Dark energy is a mysterious force that permeates all of space, pushing the universe apart and causing its expansion to accelerate. Unlike gravity, which pulls matter together, dark energy acts as a cosmic repulsion, driving galaxies and galaxy clusters away from each other at an ever-increasing rate. The nature of dark energy remains one of the biggest puzzles in modern cosmology. Scientists have proposed various theories to explain it, but none have been conclusively proven. What we do know is that dark energy makes up roughly 70% of the total energy content of the universe, exerting its influence on cosmic scales. Vacuum energy, on the other hand, is a concept from quantum field theory. It refers to the energy present in empty space due to quantum fluctuations. These fluctuations cause particles and antiparticles to constantly pop in and out of existence, even in the absence of matter. While vacuum energy and dark energy share some similarities, they are not identical. The key difference lies in their observed effects and theoretical predictions. Calculations of vacuum energy suggest it should be enormously larger than the observed value of dark energy. This discrepancy, known as the cosmological constant problem, remains unresolved and continues to challenge our understanding of the fundamental nature of the universe. Dark energy exerts a profound influence on the expansion of the universe, acting as a mysterious force that pushes everything apart. Unlike gravity, which pulls matter together, dark energy works in opposition, accelerating the expansion of space itself. This cosmic push causes galaxies and galaxy clusters to move away from each other at ever-increasing speeds. The effects of dark energy become more pronounced over vast cosmic distances. In the local universe, gravity still dominates, keeping galaxies and galaxy clusters bound together. However, on the largest scales, dark energy overcomes the attractive force of gravity, driving the accelerated expansion we observe. Astronomers discovered this accelerating expansion in the late 1990s by studying distant supernovae. They found that these stellar explosions appeared dimmer than expected, indicating that the universe was expanding faster than previously thought. This unexpected acceleration led to the proposal of dark energy as the driving force behind it. While we can observe its effects, the true nature of dark energy remains one of the biggest mysteries in modern cosmology. Scientists continue to study its properties and implications, as understanding dark energy is crucial for predicting the ultimate fate of our universe. Whether the universe will continue to expand indefinitely or eventually collapse back on itself depends largely on the behavior of this enigmatic cosmic force. The cosmological constant problem is a perplexing issue in physics that highlights the vast discrepancy between theoretical predictions and observational evidence regarding the energy density of empty space. At its core, this problem revolves around the concept of vacuum energy, which quantum field theory suggests should be enormous. However, astronomical observations indicate that the actual value of this energy is incredibly small, differing from theoretical calculations by a staggering factor of 10 to the power of 120. This enormous disparity poses a significant challenge to our understanding of the universe. On one hand, quantum mechanics predicts that empty space should be teeming with virtual particles popping in and out of existence, contributing to a high energy density. On the other hand, if this prediction were true, the universe would be expanding at an incredibly rapid rate, which is not what we observe. The cosmological constant, originally introduced by Albert Einstein in his theory of general relativity, has been repurposed to represent this mysterious energy of empty space. It is now often associated with dark energy, the unknown force causing the accelerated expansion of the universe. The fact that the observed value of the cosmological constant is so much smaller than predicted raises fundamental questions about our understanding of quantum mechanics, general relativity, and the nature of the vacuum itself. Solving the cosmological constant problem remains one of the most important challenges in modern physics. It touches upon fundamental aspects of our reality, from the smallest quantum scales to the vast expanses of the cosmos, and its resolution could lead to revolutionary insights into the nature of space, time, and the universe itself. Our understanding of vacuum energy and dark energy is poised for significant advancements in the coming years. As scientists develop more sophisticated instruments and techniques, we may uncover new insights into these mysterious forces that shape our universe. Future research could reveal a deeper connection between vacuum energy and dark energy. Some theorists propose that these phenomena might be two sides of the same coin, with vacuum energy potentially driving the accelerating expansion of the universe attributed to dark energy. If this link is confirmed, it could revolutionize our understanding of the cosmos and its underlying physics. Upcoming space missions and ground-based observatories will likely play a crucial role in refining our measurements of dark energy's effects. By observing distant supernovae and mapping the large-scale structure of the universe with unprecedented precision, scientists may be able to determine whether dark energy's strength has changed over time. This information could help distinguish between competing theories and potentially reveal new properties of this enigmatic force. Advances in quantum field theory and particle physics might also shed light on the nature of vacuum energy. As our understanding of the quantum realm deepens, we may uncover new particles or fields that contribute to the energy of empty space, potentially resolving the vast discrepancy between theoretical predictions and observed values of vacuum energy. This progress could have far-reaching implications for our understanding of the universe's past, present, and future. Symmetry in physics is a fundamental concept that describes the unchanging nature of certain aspects of a system under specific transformations. It plays a crucial role in our understanding of the universe and its laws. At its core, symmetry refers to the idea that some properties of a physical system remain constant even when the system undergoes changes or transformations. In the realm of particle physics, symmetries help scientists understand the behavior of subatomic particles and the forces that govern their interactions. For instance, the concept of charge symmetry suggests that the laws of physics would remain the same if we were to swap all particles with their antiparticles. Symmetries also extend to the larger scales of the cosmos. The principle of relativity, a cornerstone of modern physics, is itself a manifestation of symmetry. It states that the laws of physics are the same for all observers, regardless of their relative motion. This symmetry under different reference frames has profound implications for our understanding of space and time. Perhaps most importantly, symmetries in physics often lead to conservation laws. These laws, such as the conservation of energy, momentum, and charge, are fundamental to our understanding of how the universe operates. They provide a framework for predicting and explaining a wide range of physical phenomena, from the motion of planets to the behavior of quantum particles. Symmetry is a fundamental principle that underpins many of the laws of physics, shaping our understanding of the universe at its most basic level. In physics, symmetry refers to the idea that certain aspects of a system remain unchanged when subjected to specific transformations. One of the most important manifestations of symmetry in physics is the conservation laws. For example, the conservation of energy stems from the symmetry of time translation, meaning that the laws of physics remain the same regardless of when an experiment is performed. Similarly, the conservation of momentum arises from the symmetry of space translation, indicating that the laws of physics are the same everywhere in space. Symmetry also plays a crucial role in particle physics. The Standard Model, our current best understanding of fundamental particles and forces, is built on the concept of gauge symmetries. These symmetries determine the behavior of particles and the forces between them. For instance, the electromagnetic force is associated with a symmetry called gauge invariance, which explains why electric charge is conserved. At the cosmic scale, symmetry helps explain the uniformity of the universe. The cosmological principle, which states that the universe looks roughly the same in all directions and from all locations, is a form of symmetry that has profound implications for our understanding of the cosmos. This symmetry allows scientists to develop models of the universe that apply universally rather than being limited to our local region of space. Spontaneous symmetry breaking is a fundamental concept in physics that plays a crucial role in our understanding of the universe. It occurs when a system that appears to have perfect symmetry in its laws or equations suddenly transitions to a state with less symmetry. This process is spontaneous, meaning it happens naturally without external influence. To grasp this concept, imagine a pencil balanced perfectly on its tip. In theory, it could fall in any direction, maintaining symmetry. However, the slightest disturbance causes it to fall in a specific direction, breaking the initial symmetry. This simple example illustrates how a symmetric system can evolve into an asymmetric state. In the context of particle physics and cosmology, spontaneous symmetry breaking is essential for explaining phenomena such as the Higgs mechanism, which gives particles their mass. It also helps us understand phase transitions in the early universe, like the separation of fundamental forces that were once unified. The implications of spontaneous symmetry breaking extend far beyond theoretical physics. It helps explain various phenomena in condensed matter physics, such as ferromagnetism and superconductivity. By understanding this process, scientists gain insights into the fundamental nature of our universe and how it evolved from its earliest moments to its current state. Symmetry breaking played a crucial role in the early moments of our universe, shaping the cosmos we observe today. In the first fractions of a second after the Big Bang, the universe existed in a state of perfect symmetry, with all fundamental forces unified into a single, immensely powerful force. As the universe rapidly expanded and cooled, this symmetry began to break down. The process of symmetry breaking allowed the fundamental forces of nature to separate and take on their distinct characteristics. First, gravity split off from the other forces, followed by the strong nuclear force, and finally, the weak nuclear force and electromagnetism. This separation of forces was essential for the formation of matter as we know it. Symmetry breaking also led to slight imbalances between matter and antimatter in the early universe. Without this asymmetry, matter and antimatter would have annihilated each other completely, leaving behind nothing but energy. Instead, a small excess of matter remained, forming the building blocks of everything we see around us today. The concept of symmetry breaking extends beyond the separation of forces. It also explains phenomena such as the Higgs mechanism, which gives particles their mass, and the formation of cosmic structures like galaxies and galaxy clusters. By understanding symmetry breaking, scientists gain crucial insights into the fundamental nature of our universe and its origins. Supersymmetry is a theoretical concept in particle physics that proposes a fundamental connection between two types of particles, bosons and fermions. This theory suggests that every known particle has a hidden counterpart, or superpartner, with similar properties but different spin characteristics. In the context of the early universe, supersymmetry plays a crucial role in our understanding of how matter and forces behaved in the extreme conditions following the Big Bang. Scientists believe that in the intense heat and energy of the nascent cosmos, supersymmetry may have been an active, unbroken principle, with all particles and their superpartners existing in a state of perfect balance. As the universe expanded and cooled, this symmetry is thought to have broken, leading to the predominance of the particles we observe today and the apparent absence of their superpartners. This breaking of supersymmetry could explain why we see an imbalance between matter and antimatter in the universe, as well as provide insights into the nature of dark matter. While supersymmetry remains unproven, its potential to unify our understanding of fundamental forces and particles makes it a compelling area of study for physicists seeking to unravel the mysteries of the early universe and the fundamental nature of reality itself. Symmetry plays a crucial role in our understanding of the fundamental forces of nature. At its core, symmetry in physics refers to the idea that certain properties of a system remain unchanged under specific transformations. This concept has proven to be a powerful tool in unifying seemingly disparate forces. The electromagnetic force and the weak nuclear force, once thought to be entirely separate, were unified through the electroweak theory. This unification was made possible by recognizing a shared symmetry between these forces at high energies. As we observe nature at increasingly smaller scales and higher energies, more symmetries become apparent, suggesting a deeper connection between forces. The strong nuclear force, responsible for binding quarks within protons and neutrons, also exhibits symmetries that have helped physicists develop quantum chromodynamics, the theory describing this force. These symmetries, while different from those of the electroweak force, hint at a possible greater unification. Gravity, the fourth fundamental force, has proven more challenging to unify with the others. However, theoretical frameworks like string theory propose that at extremely high energies, all forces might emerge from a single, highly symmetric state. This tantalizing possibility continues to drive research in theoretical physics, as scientists seek a grand unified theory that would reveal the ultimate symmetry connecting all forces of nature. Symmetry plays a crucial role in unification theories, serving as a fundamental principle that guides physicists in their quest to understand the universe's underlying structure. In the context of particle physics and cosmology, symmetry refers to the idea that certain properties of a system remain unchanged under specific transformations. Unification theories aim to combine different fundamental forces of nature into a single, comprehensive framework. The concept of symmetry helps scientists identify common patterns and relationships between seemingly disparate phenomena. For example, the electroweak theory, which unifies electromagnetism and the weak nuclear force, relies on a symmetry principle that reveals the shared nature of these two forces at high energies. Symmetries also provide valuable constraints and predictions in theoretical models. They often simplify complex equations and reveal hidden connections between particles and forces. The standard model of particle physics, our current best understanding of fundamental particles and forces, is built upon a foundation of symmetry principles. As physicists work towards a grand unified theory or a theory of everything, symmetry continues to guide their efforts. The hope is that by uncovering more fundamental symmetries, we may eventually reveal the elegant, unified structure of the universe that underlies all of nature's forces and particles. Symmetry plays a crucial role in our understanding of the universe's origin and fundamental laws. At the moment of the Big Bang, the universe is thought to have been in a state of perfect symmetry, with all forces unified into a single, incredibly powerful force. As the universe expanded and cooled, this symmetry began to break, leading to the separation of forces and the formation of the physical laws we observe today. This concept of symmetry breaking helps explain how our complex universe emerged from an initially simple, uniform state. It provides a framework for understanding how particles gained mass and how the different forces of nature came to be distinct from one another. The Higgs mechanism, for instance, is a prime example of how symmetry breaking can lead to the emergence of new properties in particles. Furthermore, symmetries in physics often correspond to conservation laws, such as the conservation of energy or momentum. These laws are fundamental to our understanding of how the universe operates and evolves over time. By studying symmetries in particle physics and cosmology, scientists can make predictions about the behavior of matter and energy in extreme conditions, similar to those present in the early universe. Understanding symmetry also guides our search for a unified theory of physics, one that would reconcile quantum mechanics with general relativity. Such a theory could potentially explain the origin of the universe in terms of fundamental principles of symmetry, providing a deeper insight into why the universe exists and why it has the properties we observe. Time, as we understand it, began with the birth of our universe. At the moment of the Big Bang, space and time emerged together, intertwined in a way that fundamentally shapes our reality. Before this cosmic event, the concept of time as we know it simply did not exist. In the earliest moments of the universe, time behaved quite differently from how we experience it today. The extreme conditions of heat and density cause time to stretch and warp in ways that challenge our everyday understanding. As the universe expanded and cooled, time gradually settled into a more familiar form. The nature of time near the Big Bang remains a subject of intense scientific inquiry. Some theories suggest that time might have flowed in both directions or existed in a quantum state of superposition. Others propose that our universe might be part of a larger multiverse where time operates differently in each realm. Understanding time in the context of the universe's origin is crucial for unraveling other cosmic mysteries. It impacts our theories about the formation of galaxies, the distribution of matter, and even the ultimate fate of the universe. As we continue to explore these concepts, we may need to revise our fundamental ideas about the nature of time itself. As we approach the moment of the Big Bang, our understanding of time begins to unravel. The familiar ticking of seconds and minutes loses its meaning in the extreme conditions of the early universe. Near this cosmic beginning, the intense energies and densities create a realm where our current laws of physics struggle to apply. In this primordial state, space and time become so tightly intertwined that they can no longer be distinguished as separate concepts. The fabric of space-time becomes warped and distorted to such an extreme degree that our conventional notions of before and after cease to make sense. This breakdown of time as we know it is intrinsically linked to the limitations of general relativity, our best description of gravity and space-time. Quantum effects begin to dominate at these tiniest scales, introducing fundamental uncertainties that further complicate our understanding of time. The quantum foam, a concept describing the turbulent nature of space-time at the smallest scales, suggests that time might become granular or discrete rather than the smooth continuum we experience. As we get closer to the Big Bang itself, these issues compound until we reach the Planck time, the shortest measurable unit of time. Beyond this point, our current theories cannot describe what happens, and the very concept of time as a measurable, definable entity may cease to exist altogether. This limit of our understanding highlights the need for a theory of quantum gravity to fully explain the nature of time at the birth of our universe. Eternal inflation is a fascinating concept in cosmology that expands our understanding of the universe's origins and evolution. This theory proposes that our universe is just one of many bubbles in an ever-expanding cosmic foam. According to eternal inflation, the process that triggered the rapid expansion of our universe in its earliest moments continues indefinitely in other regions of space. This model challenges our traditional notion of a singular beginning for the cosmos. Instead of a single Big Bang event, eternal inflation suggests a continuous process of creation, with new universes constantly branching off from rapidly expanding regions of space. These expanding regions grow exponentially, creating pockets where inflation slows down and allows matter to coalesce into galaxies and stars, much like our observable universe. The implications of eternal inflation are profound. It suggests that our universe might be just one of countless others, each with potentially different physical laws and constants. This multiplicity of universes, often referred to as the multiverse, raises intriguing questions about the nature of reality and our place within it. Moreover, eternal inflation presents a scenario where time itself becomes a more complex concept. With no clear starting point and no foreseeable end to the inflationary process, the idea of a definitive beginning becomes blurred. This challenges our intuitive understanding of cosmic history and forces us to reconsider what we mean when we talk about the origin of the universe. The arrow of time is intimately linked to the universe's creation, stretching back to the very moment of the Big Bang. This concept describes the one-way direction of time, always moving forward, never backward. It's a fundamental aspect of our universe that emerged alongside space and matter. At the instant of the Big Bang, the universe began in an incredibly low entropy state. Entropy, a measure of disorder in a system, was at its minimum. As the universe expanded and cooled, entropy increased, establishing the arrow of time we experience. This progression from low to high entropy defines the direction of time, making the past distinct from the future. The arrow of time explains why we remember the past but not the future, why eggs break but never unbreak, and why hot coffee cools down rather than heating up spontaneously. It's a consequence of the universe's initial conditions and the fundamental laws of physics that govern its evolution. Remarkably, the arrow of time points back to a single origin point for our entire cosmos. tying our everyday experiences to the grand narrative of universal creation. It serves as a cosmic signpost, constantly reminding us of our universe's extraordinary birth and ongoing expansion. The no-boundary proposal, developed by Stephen Hawking and Jim Hartler, offers a fascinating perspective on the origin of our universe. This concept suggests that the universe has no definite starting point or boundary in time. Instead, it proposes that the early universe can be understood as a quantum state, where time and space become indistinguishable. In this model, the universe emerges smoothly from a timeless state rather than exploding into existence from a singular point. The proposal compares the beginning of the universe to the surface of the Earth. Just as we can move freely on the Earth's surface without encountering any edge or boundary, the universe's history might have no definite starting point. This idea challenges our conventional understanding of time and causality. It suggests that asking what came before the Big Bang might be meaningless, similar to asking what is south of the South Pole. The no-boundary proposal aims to provide a framework for understanding the universe's origin without relying on the concept of a definite beginning. While highly theoretical, this proposal has significant implications for our understanding of cosmic origins and the nature of time itself. It represents an attempt to reconcile quantum mechanics with gravity, offering a potential pathway to a unified theory of the universe. The concept of the universe creating its own time is a fascinating and complex idea rooted in our understanding of general relativity and the nature of space-time. When the universe began with the Big Bang, it didn't just expand into pre-existing space and time. Instead, space and time themselves came into existence with the birth of the universe. As the universe expanded and cooled in its earliest moments, the fabric of space-time itself stretched and evolved. This process effectively created the dimension of time as we know it. The expansion of space is intrinsically linked to the flow of time, with each influencing the other in a cosmic dance that continues to this day. In the very early universe, extreme conditions of energy and density led to quantum fluctuations that gave rise to the fundamental forces and particles we observe today. These quantum processes, occurring at the tiniest scales, played a crucial role in shaping the large-scale structure of spacetime. The emergence of time as a dimension can be thought of as a consequence of the universe's increasing complexity and entropy. As the universe evolved from a hot, dense state to a cooler, more spread out one, it created the conditions necessary for time to flow in the direction we perceive, from past to future, giving rise to the arrow of time we experience in our daily lives. While the Big Bang theory remains the most widely accepted explanation for the origin of our universe, scientists have proposed several alternative models to address the beginning of time. One such theory is the steady-state model, which suggests that the universe has always existed and continues to expand while maintaining a constant density. In this scenario, new matter is continuously created to fill the expanding space, eliminating the need for a singular beginning. Another intriguing concept is the cyclic model, which posits that our universe undergoes endless cycles of expansion and contraction. This theory proposes that the Big Bang was not the absolute beginning, but rather the latest in a series of cosmic rebounds. Each cycle ends with a big crunch, followed by another Big Bang, creating a perpetual cosmic dance without a definitive starting point. The ekpyrotic model offers yet another perspective, suggesting that our universe resulted from the collision of two parallel branes or membranes in a higher dimensional space. This theory attempts to explain the uniformity of the cosmos without relying on cosmic inflation, a key component of the standard Big Bang model. Lastly, some physicists explore the idea of eternal inflation, where our observable universe is just one of many bubble universes within an ever-expanding multiverse. In this scenario, the concept of a singular beginning becomes less relevant, as new universes are constantly forming and expanding in different regions of space-time. Quantum mechanics fundamentally alters our perception of time at the universe's origin. In the earliest moments after the Big Bang, when the universe was incredibly small and dense, quantum effects dominated. At this scale, time as we understand it loses its conventional meaning. The uncertainty principle, a cornerstone of quantum mechanics, suggests that at extremely small scales and high energies, time and energy become intertwined. This creates a scenario where the very concept of a precise moment of origin becomes blurred. Instead of a single point of beginning, quantum mechanics implies a range of possibilities for the universe's initial state. Furthermore, quantum fluctuations played a crucial role in the early universe. These rapid, random changes in energy levels are thought to have seeded the cosmic structure we observe today. In this quantum realm, cause and effect can become tangled, challenging our intuitive understanding of time's arrow. Quantum mechanics also introduces the possibility of tunneling, where particles can seemingly traverse barriers instantaneously. Applied to cosmology, this concept suggests that our universe might have quantum tunneled into existence from a pre-existing state, further complicating the notion of a definitive starting point in time. The anthropic principle is a thought-provoking concept in cosmology that attempts to explain why our universe appears to be finely tuned for the existence of life, particularly human life. This principle suggests that the fundamental constants and laws of physics we observe are not random, but rather seem precisely calibrated to allow for the development of complex structures, including stars, planets, and ultimately, conscious observers like ourselves. At its core, the anthropic principle posits that we should not be surprised to find ourselves in a universe that can support our existence. After all, if the universe were not capable of supporting life, we would not be here to observe it. This idea has led to fascinating discussions about the nature of our cosmos and our place within it. There are different interpretations of the anthropic principle. The weak anthropic principle simply states that the observed properties of the universe must be compatible with the existence of observers. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some point in its history. Critics argue that the anthropic principle is not a scientific explanation, but rather a tautology or an example of selection bias. Proponents, however, see it as a valuable framework for understanding the apparent fine-tuning of our universe and exploring the possibility of multiple universes or other cosmological theories that could account for our existence. The anthropic principle connects our existence as observers to the fundamental properties of the universe. This concept suggests that the physical laws and constants of nature must be compatible with the emergence of conscious life, or we would not be here to observe them. In the context of the universe's creation, the anthropic principle offers a perspective on why our cosmos appears finely tuned for life. Our universe exhibits a delicate balance of physical constants and laws that allow for the formation of stars, planets, and complex molecules necessary for life. If these constants were even slightly different, the universe might not have developed in a way that could support conscious beings. The anthropic principle posits that we observe these specific conditions because they are the only ones that could lead to our existence. Some scientists interpret this as evidence of a multiverse where countless universes exist with different physical laws, and we happen to inhabit one suitable for life. Others view it as a sign of purposeful design. Regardless of interpretation, the anthropic principle highlights the remarkable coincidence between the conditions necessary for our existence and the observed properties of our universe. This principle challenges us to consider our place in the cosmos and the nature of reality itself. It raises profound questions about the origin and purpose of the universe, pushing the boundaries of science and philosophy in our quest to understand our cosmic home. The weak and strong anthropic principles are two philosophical concepts that attempt to explain the apparent fine-tuning of our universe for life. The weak anthropic principle states that the conditions we observe in the universe must be compatible with our existence as observers. It suggests that we should not be surprised to find ourselves in a universe that allows for life, because if it did not, we would not be here to observe it. This principle does not make claims about why the universe is the way it is, only that our observations are necessarily biased by our existence. The strong anthropic principle, on the other hand, makes a bolder claim. It proposes that the universe must have properties that allow life to develop within it at some stage. This principle suggests that the fundamental constants and laws of physics are somehow constrained to be life-permitting. Some interpretations of the strong anthropic principle even argue that the universe is, in some sense, compelled to bring about the conditions necessary for conscious observers. While the weak anthropic principle is generally accepted as a logical statement, the strong anthropic principle is more controversial. Critics argue that it borders on teleology, implying a purpose or design to the universe. Proponents, however, see it as a potential explanation for the apparent fine-tuning of physical constants. These principles have implications for our understanding of the universe and our place within it. They raise questions about the nature of reality, the possibility of multiple universes, and the role of consciousness in the cosmos. As we continue to explore the universe and uncover its mysteries, the anthropic principles remain important concepts in the ongoing dialogue between science and philosophy. The anthropic principle offers a thought-provoking perspective on the apparent fine-tuning of the universe. This principle suggests that the very fact we exist to observe the universe inherently biases our observations. In other words, we can only observe a universe capable of supporting our existence. Consider the delicate balance of fundamental constants and physical laws that allow for the formation of stars, planets, and ultimately, life. The strength of gravity, the properties of subatomic particles, and the rate of cosmic expansion all seem precisely calibrated to permit our existence. The anthropic principle posits that this apparent fine-tuning is not necessarily evidence of design, but rather a consequence of our ability to observe it. This concept challenges us to consider the possibility of a vast multiverse where countless universes exist with different physical constants and laws. In this scenario, we naturally find ourselves in one of the rare universes capable of supporting life. The anthropic principle thus provides a framework for understanding our place in the cosmos without resorting to supernatural explanations. While the anthropic principle does not definitively solve the mystery of our universe's apparent fine-tuning, it offers a compelling perspective that continues to shape discussions in cosmology and philosophy. It reminds us that our very existence as observers plays a crucial role in how we interpret the fundamental nature of reality. The anthropic principle has faced several significant criticisms from scientists and philosophers alike. One major concern is that it can be seen as a form of circular reasoning, essentially stating that the universe must be compatible with our existence because we exist to observe it. Critics argue this offers little explanatory power and fails to advance our understanding of the cosmos. Another criticism is that the anthropic principle may lead to complacency in scientific inquiry. Some worry that it could be used as a catch-all explanation for any seemingly improbable features of our universe, potentially discouraging further investigation into the underlying physical mechanisms at play. Skeptics also point out that the anthropic principle relies heavily on the assumption that our form of life is the only possible one. They argue that we cannot rule out the existence of alternative forms of life or consciousness that might arise in very different conditions, making our particular set of physical constants less special than the principle suggests. Lastly, some critics view the anthropic principle as bordering on pseudoscience, arguing that it is not falsifiable and therefore falls outside the realm of scientific inquiry. They contend that while it may be an interesting philosophical concept, it lacks the rigorous testability required of scientific theories. The anthropic principle and multiverse theory are intricately connected, offering a fascinating perspective on our existence in the universe. The anthropic principle suggests that the observable universe must have properties that allow for the existence of observers like us. This idea becomes particularly relevant when considering the multiverse theory. Multiverse theory proposes that our universe is just one of many, possibly infinite, universes. Each of these universes might have different fundamental constants and laws of physics. In this vast ensemble of universes, only a small fraction would have the precise conditions necessary for life as we know it to emerge. This is where the anthropic principle comes into play. It argues that we should not be surprised to find ourselves in a universe that can support life, because we could not exist to make observations in universes that cannot support life. The multiverse theory provides a framework that makes this principle more plausible, as it offers a mechanism for the existence of numerous universes with varying properties. The combination of these ideas helps address the fine-tuning problem in cosmology. Our universe appears to be remarkably fine-tuned for life, with fundamental constants set to precise values that allow for complex structures to form. Rather than attributing this to pure chance or design, the anthropic principle in the context of a multiverse suggests that we simply happen to exist in one of the rare universes capable of supporting life, while countless others remain barren. The anthropic principle challenges our perspective on life in the universe, suggesting that the conditions we observe must be compatible with our existence as observers. This principle has profound implications for how we interpret the apparent fine-tuning of physical constants and cosmic conditions that allow life to exist. One key implication is that the rarity of life-supporting environments may not be as significant as once thought. If countless universes exist, each with different physical laws, our universe's life-friendly conditions might be a natural consequence of cosmic diversity rather than an extraordinary coincidence. The anthropic principle also raises questions about the likelihood of finding other intelligent life. If our existence is tied to specific cosmic conditions, similar conditions might be necessary for other civilizations to arise. This could mean that life is either extremely rare or potentially common in pockets of the universe with similar parameters. Furthermore, the principle encourages us to consider our role as observers more carefully. It suggests that our very ability to ask questions about the universe's nature might be intrinsically linked to the universe's properties, creating a complex relationship between observer and observed that challenges traditional scientific approaches. The anthropic principle has the potential to shape future cosmological research in profound ways. This concept suggests that the universe we observe must be compatible with the conscious life that observes it. As scientists delve deeper into the mysteries of our cosmos, they may increasingly consider how the anthropic principle affects their investigations and interpretations of data. One significant impact could be on the study of fundamental constants and laws of physics. Researchers might focus more attention on understanding why these constants appear finely tuned to allow for the existence of complex structures like galaxies, stars, and ultimately, life. This could lead to new theories exploring the possibility of multiple universes or regions with different physical laws, where only a subset allows for the emergence of conscious observers. The anthropic principle might also influence how cosmologists approach the question of dark energy and the fate of the universe. As we grapple with the accelerating expansion of space, scientists may consider whether our observations are biased by the fact that we exist in a universe hospitable to life. This could prompt new ways of thinking about the long-term evolution of the cosmos and our place within it. Furthermore, the anthropic principle could guide the search for extraterrestrial life and habitable exoplanets. By understanding the conditions necessary for our own existence, researchers may refine their criteria for identifying potentially life-bearing worlds beyond our solar system. This approach could lead to more targeted and efficient searches for biosignatures and technosignatures in the vast expanse of space. Information theory is a groundbreaking field of study that explores the fundamental nature of data, communication, and uncertainty. Developed by Claude Shannon in the mid-20th century, It provides a mathematical framework for understanding how information is quantified, stored, and transmitted. At its core, information theory deals with the concept of entropy, which measures the amount of uncertainty or randomness in a system. In the context of communication, entropy relates to the unpredictability of messages. The more unpredictable a message is, the more information it contains. This theory has far-reaching applications across various disciplines. In computer science, it forms the basis for data compression and error correction techniques. In physics, it helps explain thermodynamics and quantum mechanics. Even in biology, information theory sheds light on genetic coding and neural signaling. One of the most significant contributions of information theory is the concept of channel capacity, which defines the maximum rate at which information can be reliably transmitted over a communication channel. This idea revolutionized telecommunications and laid the groundwork for our modern digital age, influencing everything from internet protocols to smartphone technology. Information theory provides a fascinating lens through which we can examine the universe and its fundamental workings. At its core, this theory deals with the quantification, storage, and communication of information, concepts that have surprising relevance to our cosmic understanding. In the realm of physics, information theory helps us grapple with the nature of entropy and the arrow of time. The second law of thermodynamics, which states that the entropy of an isolated system always increases over time, can be reinterpreted through information theory. As systems become more disordered, they require more information to describe their state, linking the flow of time to the flow of information. Quantum mechanics, too, finds common ground with information theory. The uncertainty principle, which limits our ability to simultaneously measure certain pairs of physical properties, can be viewed as a constraint on the information we can obtain about a quantum system. This connection has led to advancements in quantum computing and cryptography, where information is encoded in quantum states. Perhaps most intriguingly, information theory has implications for our understanding of black holes. The holographic principle suggests that the information contained within a region of space can be described by information on its boundary. This concept, born from the study of black hole entropy, has profound implications for our understanding of space, time, and the nature of reality itself. The holographic principle is a groundbreaking concept in theoretical physics that suggests our three-dimensional universe might be a projection of information stored on a two-dimensional surface. This idea draws parallels with how a hologram can create the illusion of three dimensions from a flat surface. At its core, the holographic principle proposes that all the information contained within a region of space can be described by information on the boundary of that region. Imagine the universe as a sphere. The holographic principle suggests that everything happening inside this cosmic sphere can be fully represented by information on its surface. This principle has profound implications for our understanding of black holes and quantum gravity. It offers a potential resolution to the black hole information paradox by suggesting that information about objects falling into a black hole is not lost, but rather encoded on the black hole event horizon. The holographic principle challenges our perception of reality and space-time. It hints at a deeper connection between gravity, quantum mechanics, and information theory, potentially paving the way for a unified theory of quantum gravity. This principle continues to inspire new avenues of research in theoretical physics and cosmology, pushing the boundaries of our understanding of the universe and its fundamental nature. The conservation of information in the creation of the universe is a fascinating concept that delves into the heart of fundamental physics. This idea suggests that the total amount of information in the universe remains constant, even as the universe evolves and changes over time. One way to understand this is through the lens of quantum mechanics and the holographic principle. These theories propose that all the information about our three-dimensional universe might be encoded on a two-dimensional surface, much like a hologram. This encoding would preserve information even as the universe expands and evolves. Another perspective comes from the study of black holes. Stephen Hawking's work on black hole radiation suggested that information might be lost when matter falls into a black hole. However, further research indicated that this information might actually be preserved on the event horizon of the black hole, maintaining the principle of information conservation. The concept of cosmic inflation, which describes the rapid expansion of the early universe, also plays a role in information conservation. As the universe expanded, quantum fluctuations were stretched to cosmic scales, potentially preserving information from the earliest moments of the universe in the large-scale structure we observe today. Quantum information is a fascinating concept that lies at the heart of quantum computing and communication. Unlike classical information, which is based on definite states such as 0 or 1, quantum information harnesses the unique properties of quantum systems. These quantum systems can exist in multiple states simultaneously, a phenomenon known as superposition. The key difference between quantum and classical information lies in how they are stored and processed. Classical information is discrete and deterministic, meaning we can precisely measure and predict its state at any given time. Quantum information, on the other hand, is probabilistic and subject to the strange rules of quantum mechanics. This allows quantum systems to perform certain calculations and tasks exponentially faster than classical systems. Another crucial aspect of quantum information is entanglement, a phenomenon where two or more quantum particles become interconnected in such a way that the state of one particle instantly affects the state of the other, regardless of the distance between them. This property has no classical counterpart and enables unique possibilities in secure communication and data processing. While classical information is limited to bits, quantum information uses quantum bits or qubits. These qubits can represent not just 0 or 1, but any combination of the two simultaneously. This fundamental difference gives quantum information its power and potential to revolutionize computing, cryptography, and our understanding of information itself. Entropy and information are deeply intertwined concepts in our universe. At its core, entropy measures the amount of disorder or randomness in a system, while information quantifies the degree of certainty or knowledge we have about that system. As entropy increases, the amount of useful information generally decreases. In the context of the universe, entropy plays a crucial role in the flow of time and the evolution of cosmic structures. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This means that as the universe expands and evolves, it becomes more disordered and the amount of usable energy decreases. From an information perspective, this increasing entropy can be seen as a loss of information about the initial state of the universe. As cosmic structures form and interact, the original configuration becomes increasingly difficult to discern. However, this process also leads to the creation of new, complex systems that contain their own forms of information. Interestingly, some physicists propose that information might be a fundamental property of the universe, similar to matter and energy. This idea suggests that the total amount of information in the universe remains constant even as entropy increases. The challenge lies in understanding how information is preserved and transformed as cosmic processes unfold, shaping the universe we observe today. Information plays a crucial role in the ongoing debate surrounding the black hole information paradox. This perplexing issue arises from the apparent conflict between quantum mechanics and general relativity when it comes to the fate of information that falls into a black hole. Quantum mechanics dictates that information cannot be destroyed, a principle known as unitarity. However, according to Stephen Hawking's calculations, black holes emit radiation and eventually evaporate, seemingly destroying all the information about the matter that fell into them. This contradiction forms the heart of the paradox. Several theories have been proposed to resolve this conundrum, all centering on the preservation or retrieval of information. One idea suggests that information might be encoded on the event horizon of the black hole, much like a hologram. This concept, known as the holographic principle, proposes that all the information about the interior of a region of space can be described by information on its boundary. Another possibility is that information slowly leaks out through Hawking radiation over time. Some physicists argue that subtle correlations in this radiation could carry encoded information about everything that fell into the black hole. However, the exact mechanism for how this information might be preserved and transmitted remains a subject of intense study and debate among theoretical physicists and cosmologists. Information theory offers a fascinating lens through which we can examine the fundamental nature of reality. At its core, this branch of science deals with the quantification, storage, and communication of information. When applied to our understanding of the universe, it suggests that reality itself might be composed of information at its most basic level. Consider the concept of entropy, a key principle in both information theory and thermodynamics. In information theory, entropy measures the amount of uncertainty or randomness in a system. This aligns with the idea that the universe tends towards increasing disorder over time. By viewing reality through this informational framework, we can explore how the flow and organization of information might shape the very fabric of existence. Quantum mechanics, too, finds interesting parallels with information theory. The behavior of subatomic particles can be described in terms of probability and information states. This connection hints at a deeper relationship between information and the quantum world, suggesting that the act of measurement or observation might be fundamentally about gaining or transferring information. Furthermore, information theory could help us tackle some of the most perplexing questions in physics, such as the nature of black holes and the holographic principle. These concepts propose that the information contained within a region of space can be described by information on its boundary, challenging our traditional notions of dimensionality and the structure of space-time itself. By applying information theory to these cosmic puzzles, we might unlock new insights into the underlying mechanics of our universe. The question of the universe's origin has profoundly influenced philosophical thought throughout human history. This fundamental inquiry challenges our understanding of existence itself and forces us to confront the limits of human knowledge. Many philosophers have grappled with the concept of a beginning to everything, leading to deep discussions about causality and the nature of time. The idea that the universe might have a starting point raises questions about what came before and what caused it to come into being. This line of thinking has given rise to various cosmological arguments for the existence of a divine creator or a first cause. The origin of the universe also ties into debates about determinism and free will. If the universe began from a singular point with set physical laws, some argue that all subsequent events could theoretically be predicted, challenging notions of human agency and moral responsibility. Conversely, others point to quantum mechanics and its inherent uncertainties as potential sources of true randomness and free will. Furthermore, contemplating the universe's beginning has led philosophers to explore concepts of infinity and eternity. The possibility of a universe without a beginning challenges human intuition and has sparked discussions about the nature of existence itself. These questions continue to drive philosophical inquiry, blending metaphysics, epistemology, and ethics in the ongoing quest to understand our place in the cosmos. The concept of a self-creating universe challenges our traditional understanding of causality, pushing the boundaries of what we consider possible in the cosmos. This idea suggests that the universe might have come into existence without an external cause, fundamentally altering how we think about the origins of everything we know. In classical physics, every effect has a cause that precedes it in time. However, when we consider the birth of the universe itself, this principle becomes problematic. If the universe includes all of space and time, then there can be no before the universe to contain a cause. This leads us to contemplate the possibility that the universe might be its own cause, a concept that defies our everyday experience of cause and effect. Quantum mechanics offers some intriguing possibilities for how this might work. At the quantum scale, events can occur without definite causes, such as the spontaneous appearance of virtual particles. Some theories propose that the entire universe might have emerged as a quantum fluctuation, essentially popping into existence from nothing. This self-creating scenario would mean that the very laws of physics, including causality itself, could have emerged along with the universe. In this view, asking what caused the universe becomes as meaningless as asking what is north of the North Pole. The implications are profound, suggesting that our universe might be just one of many possible configurations that could spontaneously arise, each with its own set of physical laws. The concept of a universe emerging from nothing presents a significant challenge to many traditional religious beliefs. This idea, rooted in scientific theories and observations, suggests that our cosmos could have spontaneously come into existence without the need for a divine creator. Many religions teach that the universe was created by a supreme being or God through deliberate action. However, scientific models propose that quantum fluctuations in a state of nothingness could give rise to the universe we observe today. This explanation does not require the intervention of a supernatural force, directly contradicting the creation stories found in various religious texts. Furthermore, the idea of a universe from nothing raises questions about the nature of existence itself. If our universe can emerge spontaneously, it implies that the fundamental laws of physics might exist independently of any conscious entity. This notion challenges the traditional view of a god as the ultimate source of all natural laws and order in the cosmos. The concept also impacts ideas about the purpose and meaning of the universe. While many religions teach that the cosmos was created with specific intent, a universe from nothing suggests that our existence might be the result of random quantum events rather than divine planning. This perspective can profoundly affect how people view their place in the universe and the nature of reality itself. The concept of multiple universes, often called the multiverse, sparks numerous philosophical questions that challenge our understanding of reality and existence. One fundamental question is whether our universe is unique or just one of countless others. This idea forces us to reconsider our place in the cosmos and the significance of our existence. Another intriguing question is whether these other universes have different laws of physics. If so, what determines these laws, and why does our universe have the specific set of rules it does? This leads to the anthropic principle, which suggests that our universe appears fine-tuned for life because we can only observe a universe capable of supporting our existence. The multiverse theory also raises questions about free will and determinism. If every possible outcome of every decision occurs in different universes, does that mean our choices are meaningless? Or does it imply that free will is an illusion and our actions are predetermined by the initial conditions of our particular universe? Lastly, the multiverse concept challenges our notions of creation and purpose. If infinite universes exist, does that negate the need for a creator or a grand design? Or does it point to an even more complex and awe-inspiring reality beyond our current comprehension? These questions continue to fuel debates among philosophers, scientists, and theologians alike. The concept of a self-creating universe challenges our traditional notions of causality and determinism, which in turn impacts our understanding of free will. In a self-creating universe, the very laws of physics and the initial conditions might emerge from the universe itself, rather than being set by an external force or predetermined at the beginning of time. This idea introduces a level of intrinsic randomness and unpredictability into the fabric of reality. If the universe can create itself, it suggests that fundamental aspects of existence might not be fully determined, opening up possibilities for genuine novelty and spontaneity at the deepest levels of nature. For free will, this has profound implications. In a purely deterministic universe, one could argue that all our actions are predetermined by prior causes, leaving no room for true free will. However, a self-creating universe with inherent indeterminism could provide the necessary wiggle room for genuine choice and agency to emerge. Yet, this also raises new questions. If the universe and its laws are self-creating, how does this process interact with our decision-making? Are our choices influenced by these self-creating processes, or do we participate in them? The concept of a self-creating universe doesn't definitively solve the free will debate, but it does reshape the landscape of possibilities, challenging us to reconsider the nature of choice, determinism, and the fundamental structure of reality itself. The concept of an infinite multiverse raises profound ethical questions that challenge our understanding of morality and existence. If there are infinite versions of ourselves making every possible decision, how do our choices in this universe matter? This idea could lead to a sense of moral nihilism, where individuals feel their actions have no consequences because another version of themselves will always make the opposite choice. However, we must consider that even in an infinite multiverse, our experiences and decisions in this particular universe remain uniquely important to us and those around us. The impact of our choices on the people we interact with and the world we inhabit is real and significant, regardless of what may be happening in other universes. Another ethical implication involves the question of responsibility. If every possible decision is made somewhere in the multiverse, does that absolve us of moral responsibility for our actions? This line of thinking could be dangerous, potentially leading to reckless or harmful behavior justified by the belief that it was bound to happen somewhere. Ultimately, the ethical stance that seems most reasonable is to act as if our universe is the only one that matters. This approach allows us to maintain moral responsibility and make meaningful choices while acknowledging the mind-bending possibilities of a multiverse. It encourages us to focus on creating positive outcomes in the universe we can directly influence, rather than becoming paralyzed by the infinite possibilities beyond our reach. The origin of the universe profoundly shapes our understanding of existence and our place within it. The Big Bang Theory, our current best explanation for the universe's beginning, suggests that all matter, energy, space, and time emerged from an incredibly dense, hot state about 13.8 billion years ago. This concept of a definite starting point for everything we know challenges us to contemplate our significance in the grand cosmic narrative. Knowing that our universe had a beginning prompts us to question whether it might have an end and what that could mean for life as we know it. It also raises the possibility that our universe might be one of many, existing in a vast multiverse. These ideas can either diminish our sense of importance or inspire us to create meaning in a potentially finite existence. The fact that the universe has evolved from simple elements to complex structures, eventually giving rise to conscious beings like ourselves, suggests a kind of cosmic progress. This progression from simplicity to complexity might imply that the development of intelligence and self-awareness is a natural outcome of universal processes. Such a perspective could imbue our existence with a sense of purpose as we strive to understand and perhaps even shape the future of cosmic evolution. Moreover, the realization that we are made of elements forged in the hearts of stars connects us intimately to the cosmos. This understanding of our physical link to the universe's history can foster a profound sense of belonging and responsibility. It may drive us to explore, learn, and care for our cosmic home, giving us purpose as conscious participants in the ongoing story of the universe. The concept of a self-creating universe challenges traditional philosophical and theological views, but several frameworks have emerged to explore this intriguing possibility. Naturalism, which posits that everything arises from natural properties and causes, aligns well with the idea of a universe that comes into being without external intervention. This perspective suggests that the fundamental laws of physics could be sufficient to explain the origin of our cosmos. Another framework that accommodates a self-creating universe is scientific materialism. This view holds that physical matter is the only reality, and that all phenomena, including consciousness, are the result of material interactions. In this context, the universe could be seen as a complex system that emerges from fundamental physical processes. Process philosophy, developed by thinkers like Alfred North Whitehead, offers a unique perspective on a self-creating universe. This approach views reality as an ongoing process of becoming, rather than a static state of being. It suggests that the universe is continuously creating itself through the interplay of events and experiences, aligning well with the idea of cosmic self-creation. Lastly, some interpretations of Eastern philosophies, particularly certain schools of Buddhist thought, propose a cyclical view of the universe that could be compatible with self-creation. These perspectives suggest that the universe goes through endless cycles of creation and destruction, with each cycle emerging from the conditions set by the previous one, potentially without the need for an external creator. Our quest to understand the universe's origin faces several significant challenges. The cosmic microwave background radiation, the oldest light we can observe, only reveals the universe as it existed about 380,000 years after the Big Bang. This leaves us with a cosmic blind spot for the earliest moments of our universe's existence. The extreme conditions of the early universe also pose difficulties for our current theories and observational tools. The laws of physics, as we know them, break down when we try to describe what happened in the first fraction of a second after the Big Bang, known as the Planck era. Our most advanced particle accelerators and detectors cannot replicate or measure the incredible energies present during this time. Another limitation is the vast scale of the universe itself. Even with our most powerful telescopes, we can only directly observe a fraction of the cosmos. The expansion of the universe means that some regions are now so far away that their light will never reach us, creating a cosmic horizon beyond which we cannot see. Lastly, the nature of dark matter and dark energy, which together make up about 95% of the universe's content, remains a mystery. Our limited understanding of these components hinders our ability to fully grasp the universe's past and future evolution, including its origin. Despite these challenges, scientists continue to push the boundaries of knowledge, developing new theories and technologies to peer ever closer to the birth of our cosmos. Future technological advancements promise to revolutionize our understanding of cosmic origins. As we develop more powerful telescopes and observatories, both on Earth and in space, we will be able to peer deeper into the universe and further back in time. These advanced instruments will allow us to observe the earliest galaxies and stars, providing crucial data about the conditions of the early universe. Improvements in particle accelerators and detectors will enable scientists to recreate and study conditions closer to those present during the Big Bang. This will help us refine our models of the universe's first moments and potentially uncover new physics that could explain fundamental aspects of our cosmos. Quantum computing advancements may allow us to process vast amounts of astronomical data more efficiently, leading to new insights and discoveries. These computers could simulate complex cosmic phenomena with unprecedented accuracy, helping us better understand the formation and evolution of galaxies, stars, and planets. Furthermore, breakthroughs in gravitational wave detection technology will open up new avenues for studying cosmic events. By capturing gravitational waves from the early universe, we may gain direct evidence of cosmic inflation and other processes that shaped our universe in its infancy, significantly enhancing our understanding of cosmic origins. Artificial intelligence is revolutionizing cosmological research, offering powerful tools to analyze vast amounts of data from telescopes and space missions. These advanced algorithms can identify patterns and anomalies that might escape human observation, potentially leading to groundbreaking discoveries about the universe. One key application of artificial intelligence in cosmology is in the analysis of cosmic microwave background radiation, the afterglow of the Big Bang. Machine learning algorithms can sift through this ancient light, detecting subtle variations that could reveal new insights into the early universe and the formation of cosmic structures. artificial intelligence is also proving invaluable in the search for exoplanets. By processing the immense data sets from space telescopes, these systems can identify the telltale signs of planets orbiting distant stars, even when those signals are extremely faint. This capability has already led to the discovery of numerous potentially habitable worlds beyond our solar system. Furthermore, artificial intelligence is aiding in the development of more accurate cosmological models. By simulating complex interactions between dark matter, dark energy, and visible matter, these systems help scientists refine their understanding of the universe's structure and evolution. As artificial intelligence continues to advance, its role in unraveling the mysteries of the cosmos is likely to expand, potentially leading to discoveries that reshape our understanding of the universe. Scientists are constantly devising new experiments and observations to test our understanding of the universe. One intriguing approach involves the search for gravitational waves from the early universe. These ripples in space-time, predicted by Einstein's theory of general relativity, could provide valuable insights into cosmic inflation and the nature of gravity itself. Another promising avenue is the hunt for dark matter particles. Advanced detectors buried deep underground or in space are designed to capture the elusive interactions of these mysterious particles, which are thought to make up a significant portion of the universe's mass. Success in this endeavor would not only confirm the existence of dark matter, but also shed light on its properties and distribution. Astronomers are also eagerly awaiting the next generation of powerful telescopes, both on Earth and in space. These instruments will peer further into the cosmos and with greater clarity than ever before, potentially revealing the first stars and galaxies formed after the Big Bang. Such observations could help refine or challenge our models of cosmic evolution and structure formation. In the realm of particle physics, increasingly powerful particle accelerators are pushing the boundaries of our knowledge. By recreating conditions similar to those in the early universe, these experiments could uncover new particles or forces, potentially bridging the gap between quantum mechanics and general relativity. Each new discovery or null result brings us closer to a more complete understanding of the fundamental nature of reality. The discovery of extraterrestrial life would profoundly reshape our understanding of the universe's origin and our place within it. Such a monumental finding would suggest that life is not unique to Earth, opening up new avenues of exploration into how life emerges and evolves across cosmic environments. If we were to find microbial life on Mars or within the subsurface oceans of icy moons like Europa or Enceladus, it would indicate that life can arise in diverse conditions. This would lend support to the idea that the universe might be teeming with simple life forms, challenging our notions of what constitutes a habitable environment. The detection of complex or intelligent life elsewhere in the cosmos would have even more far-reaching implications. It would force us to reconsider the likelihood of life developing advanced capabilities and potentially suggest that intelligence might be a common outcome of evolution under the right circumstances. This could lead to new theories about the role of life and consciousness in the cosmic order. Furthermore, studying extraterrestrial life forms could provide crucial insights into the chemical and physical processes that gave rise to the universe as we know it. By comparing the biochemistry of alien life to our own, we might uncover universal principles underlying the emergence of life, potentially shedding light on the fundamental nature of existence itself. Cosmologists continue to grapple with several fundamental questions about the universe's creation. One of the most pressing is the nature of the Big Bang itself. While we have strong evidence that the universe expanded rapidly from an incredibly hot, dense state, we still don't fully understand what triggered this expansion or what existed before it. Another major question concerns the concept of cosmic inflation. This theory suggests that the universe underwent a period of exponential expansion in its earliest moments, but the exact mechanism driving this inflation remains unclear. Scientists are still searching for definitive evidence to confirm or refute this idea. The origin of dark energy, which appears to be accelerating the expansion of the universe, is another significant mystery. We can observe its effects, but we don't know what it is or why it exists. Similarly, the nature of dark matter, which seems to hold galaxies together, remains elusive despite decades of searching. Lastly, cosmologists are still working to reconcile quantum mechanics with general relativity, especially in explaining the extreme conditions present at the moment of the Big Bang. This quest for a theory of quantum gravity represents one of the most challenging and important pursuits in modern physics, potentially holding the key to understanding the very birth of our universe. Our understanding of the universe's origin is poised for significant advancements in the coming decades. As technology improves and new observational tools come online, scientists will be able to peer further back in time, closer to the moment of the Big Bang. One area of potential breakthrough is in the study of gravitational waves. These ripples in space-time, first detected in 2015, offer a new way to observe cosmic events. Future gravitational wave detectors may allow us to detect echoes from the earliest moments of the universe, providing crucial data about its birth and early expansion. Advances in particle physics, particularly at facilities like the Large Hadron Collider, could shed light on the nature of dark matter and dark energy. These mysterious components, which make up the majority of the universe, remain poorly understood. Unraveling their secrets could dramatically reshape our cosmic origin story. Furthermore, improved observations of the cosmic microwave background radiation, the afterglow of the Big Bang, may reveal new details about the early universe. This could potentially confirm or challenge current theories about cosmic inflation, the theorized period of rapid expansion immediately following the Big Bang. Such discoveries could fundamentally alter our understanding of how the universe began and evolved into its current state. The exploration of the universe's creation demands a fusion of diverse scientific disciplines. Combining astrophysics with quantum mechanics offers a powerful approach to understanding the earliest moments of our cosmos. These fields together can shed light on the quantum fluctuations that may have seeded the universe's structure. Cosmology and particle physics intersect at the study of the Big Bang, with particle accelerators recreating conditions similar to those in the early universe. This collaboration has already yielded fascinating insights into the behavior of matter at extreme energies and could reveal more about the fundamental forces that shaped our universe. Advances in computer science and artificial intelligence are revolutionizing how we process and analyze vast amounts of astronomical data. Machine learning algorithms can identify patterns and anomalies that might escape human observers, potentially uncovering new clues about cosmic evolution. Astrobiology merges biology with astronomy, chemistry, and geology to study the potential for life beyond Earth. This interdisciplinary field could provide crucial insights into the conditions necessary for life to emerge, offering a new perspective on the universe's capacity for complexity and self-organization. By combining these diverse approaches, scientists can paint a more comprehensive picture of our cosmic origins. Cognitive biases significantly influence our understanding of the universe's origin, often leading us to misinterpret or oversimplify complex cosmological concepts. Our brains, evolved for survival in a very different environment, struggle to grasp the immense scales and counterintuitive phenomena involved in cosmic origins. One prominent bias affecting our comprehension is the tendency to seek patterns and causality, even where none exist. This can lead us to draw incorrect conclusions about cosmic events or to oversimplify the intricate processes involved in the early universe. Additionally, our innate preference for narratives and stories can cause us to construct overly simplistic explanations for complex phenomena, potentially overlooking crucial scientific details. Confirmation bias also plays a role, as we tend to favor information that aligns with our existing beliefs about the universe's origin. This can make it challenging to accept new scientific discoveries that contradict our preconceptions. slowing down our collective understanding of cosmic origins. Moreover, our difficulty in conceptualizing vast timescales and distances can lead to misconceptions about the age and size of the universe. To overcome these biases, scientists employ rigorous methodologies and peer review processes. However, for the general public, awareness of these cognitive limitations is crucial. By recognizing our biases, we can approach cosmological concepts with a more open mind, enabling a deeper and more accurate understanding of the universe's beginnings. Mathematics serves as the universal language of the cosmos, providing a powerful framework for decoding the mysteries of our universe's origins. It allows scientists to model complex phenomena, make precise predictions, and unravel the fundamental laws governing reality. Through mathematical equations, we can describe the behavior of subatomic particles, the evolution of stars, and even the expansion of the universe itself. In cosmology, mathematics enables us to extrapolate backwards in time, piecing together the story of our cosmic origins. It helps us calculate the age of the universe, predict the abundance of elements formed in the early moments after the Big Bang, and understand the intricate dance of matter and energy that led to the formation of galaxies and large-scale structures. However, mathematics also has its limitations when it comes to understanding cosmic origins. As we approach the earliest moments of the universe, our current mathematical models break down. The extreme conditions of the Big Bang, where the laws of physics as we know them may not apply, present a significant challenge. Additionally, mathematical models often rely on assumptions and simplifications, which may not fully capture the complexities of reality. Furthermore, mathematics cannot provide direct observational evidence. While it can guide our understanding and make predictions, it must always be validated through empirical observations and experiments. The quest to understand our cosmic origins requires a delicate balance between mathematical theory and observational evidence, each informing and refining the other in our ongoing journey of discovery. Language and cultural perspectives play a crucial role in shaping our understanding of the universe's creation. Different cultures have developed unique cosmologies and creation myths that reflect their worldviews, values, and experiences. These narratives often use metaphors and symbols specific to their environment and way of life, influencing how people conceptualize the origins of the cosmos. In Western scientific discourse, the language used to describe the universe's creation often employs terms like Big Bang and cosmic inflation, which reflect a particular cultural and scientific perspective. These concepts, while based on empirical evidence, still carry cultural connotations that may not resonate with all societies. Indigenous cultures, for example, often have creation stories that emphasize the interconnectedness of all living things and the cyclical nature of existence. These perspectives can lead to a different conceptualization of the universe's origins, one that may not align with the linear, time-bound models prevalent in modern cosmology. The limitations of human language itself also influence our ability to conceptualize and communicate ideas about the universe's creation. Many of the concepts in modern cosmology, such as the nature of time before the Big Bang or the existence of multiple universes, push the boundaries of our linguistic and cognitive capacities. This challenge highlights how our understanding of cosmic origins is inevitably filtered through the lens of our language and cultural background. Scientific inquiry into the universe's origin faces several significant challenges. Our current understanding is limited by the observable universe, which represents only a fraction of the entire cosmos. Beyond this boundary, we cannot directly observe or measure phenomena, leaving gaps in our knowledge. The singularity at the heart of the Big Bang theory presents another hurdle. Our current physical models break down when describing the extreme conditions of the early universe, making it difficult to explain what happened in the first fractions of a second after the Big Bang. Technological limitations also constrain our ability to probe the earliest moments of the universe. While advanced instruments like space telescopes and particle accelerators have greatly expanded our knowledge, they still fall short of directly observing the universe's birth. Furthermore, the nature of dark matter and dark energy remains elusive, despite their significant role in the universe's composition and expansion. Unraveling these mysteries could provide crucial insights into the cosmos's origin and evolution, but current methods struggle to detect and study these phenomena directly. The nature of consciousness profoundly influences our ability to comprehend cosmic origins. Our conscious minds, evolved on Earth to navigate everyday experiences, often struggle to grasp the immense scales and abstract concepts involved in understanding the universe's beginnings. Human consciousness tends to perceive time linearly and space in 3 dimensions, yet cosmic origins involve concepts like the Big Bang, where time and space themselves came into existence. This fundamental mismatch between our intuitive understanding and the reality of cosmic origins creates significant cognitive hurdles. Furthermore, our consciousness is limited by the information our senses can perceive. We cannot directly observe the early universe or the processes that led to its formation. Instead, we rely on indirect evidence and complex mathematical models, which can be challenging for human consciousness to fully internalize. However, consciousness also provides us with the capacity for abstract thought and imagination, allowing us to push beyond our immediate perceptions. Through scientific inquiry and theoretical frameworks, we have managed to expand our understanding far beyond what our everyday consciousness can readily comprehend, gradually unveiling the mysteries of cosmic origins. Intuition plays a crucial role in developing theories about the universe's creation, often serving as the spark that ignites groundbreaking scientific discoveries. Scientists frequently rely on their intuitive understanding of natural phenomena to formulate initial hypotheses and guide their research. This intuitive approach allows researchers to make creative leaps and connections that might not be immediately apparent through pure data analysis alone. Many of the most revolutionary theories in cosmology began as intuitive insights. For example, Albert Einstein's theory of general relativity stemmed from his intuitive understanding of gravity and space-time. His famous thought experiments, such as imagining riding alongside a beam of light, led to profound revelations about the nature of the universe. However, intuition alone is not sufficient in scientific inquiry. It must be rigorously tested and supported by empirical evidence. The scientific method requires that intuitive ideas be subjected to careful observation, experimentation, and peer review. This process helps separate valid intuitions from misconceptions and ensures that theories about the universe's creation are grounded in observable reality. In the realm of cosmology, intuition often guides scientists to ask the right questions and explore unconventional ideas. It allows them to envision possibilities beyond current knowledge, pushing the boundaries of our understanding. As we continue to unravel the mysteries of the cosmos, the interplay between intuition and rigorous scientific investigation remains a powerful tool in our quest to comprehend the origins of the universe. The universe presents us with a fascinating paradox. On one hand, we have discovered elegant and seemingly simple physical laws that govern the behavior of matter and energy. On the other, we observe a cosmos of staggering complexity and diversity. This apparent contradiction between simplicity and complexity is a central theme in our understanding of the universe. The fundamental laws of physics, such as gravity, electromagnetism, and the strong and weak nuclear forces, can be described with remarkable conciseness. These laws apply universally, from the smallest subatomic particles to the largest cosmic structures. Their simplicity and consistency across vast scales suggest an underlying order to the universe. However, these simple rules give rise to intricate and often unpredictable outcomes when applied to large systems over long periods. The interaction of countless particles following these basic laws leads to the emergence of complex structures and phenomena. Stars, planets, galaxies, and even life itself are all products of these fundamental interactions playing out over billions of years. This reconciliation between simplicity and complexity is perhaps best understood through the concept of emergence. Simple rules, when applied repeatedly and allowed to interact, can produce astonishingly complex results. The universe we observe today, with all its richness and diversity, is the cumulative result of these simple laws acting across cosmic timescales, creating a tapestry of complexity that continues to astound and inspire us. Gödel's incompleteness theorems shake the foundations of mathematical certainty and have profound implications for our understanding of the universe. These theorems, developed by logician Kurt Gödel in the 1930s, demonstrate that within any consistent mathematical system, there are statements that can neither be proved nor disproved using the rules of that system. This discovery challenges the idea that we can fully describe and understand the universe through mathematics alone. It suggests that there may always be truths about the cosmos that lie beyond our ability to prove, no matter how advanced our mathematical and scientific knowledge becomes. This limitation extends to our theories of physics and cosmology, implying that a complete, self-contained theory of everything might be fundamentally impossible. The incompleteness theorems also raise questions about the nature of truth and knowledge in science. They indicate that our understanding of the universe may always be incomplete or subject to revision. This doesn't mean that scientific progress is futile, but rather that we should approach our theories with humility, recognizing that there may always be aspects of reality that elude our grasp. Furthermore, these theorems have sparked discussions about the relationship between human cognition and the universe we seek to understand. They suggest that the limitations of our logical systems might reflect inherent limitations in how we, as beings within the universe, can comprehend its totality. This philosophical implication invites us to consider whether a complete understanding of the cosmos is achievable, or if the very nature of existence includes elements that will forever remain mysterious.